the first invited speaker of this evening session, Dr. Naseemuddin, scientist at Institute for Infocom Research, A-Star, Singapore. Naseemuddin received his BSc and MSc degrees from Jamia Millia Islamia Central University, New Delhi in the year of 94 and 96. Then he did his MTech with a specialization in microwave electronics and PhD degrees both from University of Delhi in 1998 and 2004 respectively. Dr. Naseemuddin has worked as a senior research fellow during 1999 to 2003 in DST-sponsored project on optical control of passive microwave devices and Council of Scientific and Industrial Research (CSIR) Government of India Senior Research Fellowship in Engineering Science for the project entitled Investigation of Microstrip Antennas as a Sensor for Determination of Complex Dielectric Constant of Materials at the Department of Electronic Science, University of Delhi. He has worked as an Australian postdoctoral research fellow during 2004 to 2006 in awarded Discovery Project grant from Australian Research Council for project entitled Microwave Sensor based on Multilayered Microstrip Patch and Line Resonator at the Macquarie University, Australia. Currently, he is a scientist at the Institute for Infocom Research, Academy for Science Research, Science Technology and Research, A-Star, Singapore. He has published over 190 technical papers in journals and conference proceedings on microstrip-based microwave antennas and components. He has been filed for antenna patents, applications, and several antenna technology licenses to companies. His research interests include multi-layered microstrip-based structures, millimeter wave antennas, RFID antennas, antennas for GPS and GNSS application, metamaterial-based microstrip antennas, beam-forming and beam-steering antennas, RF energy harvesting systems, circularly polarized microstrip antennas, and small antennas for TV white space communication. He is a senior member of IEEE and IEEE Antenna and Propagation Society and executive committee member of IEEE MTT, IEEE AP chapter, and IEEE CRFID chapter Singapore. He has been organizing committee members of international and national conferences related to antennas and propagation. He was awarded a senior research fellowship from Council of Scientific and Industrial Research, Government of India in Engineering Science during 2001 to 2003. A Discovery Project Fellowship from Australian Research Council during 2004 to 2006. A Young Scientist Award from International Union of Radio Science, RC, in 2005. And Singapore Manufacturing Federation Award with Project Team in 2014. With this, I welcome you and invite you as the first speaker of this session, Dr. Naseemuddin. Please start the session.
Thank you so much for a nice and long introduction about me. I would like to thank Professor Taimur, Professor Antar, Professor Ashok Day, NIT Silchar management team, and the Energy Harvesting Workshop organizing team for inviting me and to be here. And I also congratulate the workshop organizing team for organizing the wonderful and successful conference on energy harvesting system. Hello everyone, good night, good evening, and good afternoon. As you know, this is the how to upload the.
Sir, on bottom side of your screen, there is an option, bottom corner, present now.
Okay.
You click on that one and click entire screen.
Okay.
Then it will be, yes, share screen.
But I cannot find the share.
No.
Okay.
Click on bottom. Yes. I think it is coming. Yeah. Make it slideshow, sir.
Okay. As you know, this is the last day of the conference.
Sir, last on the bottom side, one icon is highlighted. You please hide that one.
Which one? Hide, right?
Yes, please.
Now okay?
Yeah. Now it is okay. Okay.
As today is the last day of this workshop, and my talk around about the circular polarized antenna for energy harvesting system. So last couple of days, you have heard a lot of expert speaker about the energy harvesting system and antenna also. Uh, Professor Antar presented the various type of the DR antenna, and Alfon have presented the about the metamaterial or meta surface based the harvester, how we can use the meta surface to harvest the energy. And also Ashok Day presented the detail about the retina design, and also the Kanujia, Professor Kanujia also presented the design and analysis of the uh, retinas. So today I just changed something differently, circular polarized antenna for energy harvesting. So these are the outline of my presentation. So I will give you the brief introduction of energy harvesting, because you have I think now knowledge of about the energy harvesting, because most of the expert speakers speak about this. And I will give some design consideration, how to design the energy harvesting system, and then energy harvesting sources, what are the available energy harvesting sources, and different antenna configurations. And I will also discuss the polarization, what is the effect of the polarization of the energy harvesting system. And then I will present the circular polarized antenna for energy harvesting system. One example is the GSM band 900, and other one is the dual band GSM 900 and Wi-Fi 2.4 gigahertz. And third, we have designed some beam switching or beam steering antenna for wireless power transfer to use as a energy harvesting system. And finally, I will conclude my today presentation. So as you know, energy is everywhere. So we have to smartly collect the whatever ambient energy surrounding us, collect and convert to the electrical energy for low power devices. This is the main aim of the energy harvesting system. So if you know, the energy is everywhere in different sources like TB and um, TB, Wi-Fi router, mobile, and we have the TB tower, mobile tower, or satellite, and 3D, 4G, RFID reader. You have the different type of field surrounding. So how to collect the all kind of waves and convert it to electrical energy or DC to charge up the low power devices. This is the main aim of the energy harvesting system. As you know, the nowadays now the power of the sensor or low power devices drastically reducing, and number of the wireless devices increasing. And if you know this one, the energy harvested power also increasing, because we have the lot of sources now, every day increasing drastically. Every day the mobile base station, wireless devices, and now the 5G coming. So every day wireless devices increasing, and um, in semiconductor technology improvement. So while the power consumption of the device is decreasing, so I think in coming few years or 5 years later, I think we can reach the, how to select the pointer. We can combine this graph. Once this graph combined, then we can use the energy harvesting system anywhere. You can charge your low power devices, sensor, RFID tag, or temperature sensor, whatever. There are a lot of sensor, because connectivity and IoT needs a lot of sensor. So we need to power up of this sensor. So I think in future, most of IoT sensor and wireless sensor or some different type of sensor monitoring, health monitoring, and wireless network sensor, low power sensor, IoT, smart home building. You need in a smart building lot of sensor. So how to power up these sensor? So in future, I hope we can use the energy harvesting system to charge of these type or these low power devices. So as you know, the energy harvesting system is need the two domain expertise. One is the EM electric field and antenna, etc. And other is the electronics devices. This is the interface between two domain. So if you want to design the efficient energy harvesting system, so you should know the knowledge of both domain. The EM field, what is the polarization, what kind of antenna, or what is the uh, available energy source, and how to measure these sources, power density, etc. And in electric side, we have to know the and rectifier and impedance matching. This interface, I think, mainly depend on the impedance matching. Impedance matching is the very important to match the antenna and rectifier, because rectifier is a non-linear device. If you increase the power, change the power or change the frequency, change the load, impedance matching, the impedance of the rectifier change, the mismatch. So how to design the wide impedance matching or frequency independent matching or power independent matching or whatever load independent. This is the very challenging. This interface part is very challenging. So that's you have to need the like tunable matching to match the antenna rectifier. Then you can transfer power. If you not mismatch, then you cannot uh, transfer the power to rectifier. And if rectifier no power, then you cannot get the power. So this part is very important. And I think man is this part. If you design very nicely this part and match the antenna with rectifier, you can get the maximum power. So you have to have two team with both domain to design the efficient system. Because for the direct, you have the non-RF source, so very easy to design antenna. Just to you have the D, you can calculate the power available for rectifier. But if you change the power, the impedance matching is also changed. Then you need to change the impedance matching, or you have to design wideband matching to design the efficient antenna. So these are the some design consideration for development the efficient RF energy harvesting system. If you want to design the energy harvesting system, you have to select where you want to use this RF energy system. Then that place and what is the application, what is the power required for power of the sensor or other low power devices. Then you have to survey the what kind of the power you have the surrounding energy harvesting system, and you have to measure the power. Based on that, you can design the antenna, what is the frequency, and this based on that you need a wide band or multi-band or wide beam. If you have the non-source, you need to directional antenna. Just to design directional antenna, you can get the maximum power. And based on that, you can choose the efficient rectifier topology, like full wave, half wave, or voltage doubler, etc. to to get the um, high output voltage. And then you have to design matching circuit also, and the harvested ambient RF energy from the multiple source. If the power is very low, then you can design multiple sources, or you can design multiple rectifier to receive the more power and then combine. You have the like RF combining, DC combining to enhance the further output voltage or power. These are the very important design consideration to be considered for designing the energy harvesting system. Whenever you start the designing of the RF energy harvesting system, then you have to think these questions: what the suitable abundant frequency band, multi-band or wideband, narrowband, and available power levels. Based on that, you can design the antenna, receiving antenna. High, you need a high gain, wideband or multi-band, and also it depends on the application where you want to install the harvesting system. Uh, Sometime if you need the healthcare, you need very small antenna, and so no choice there. And type of the which type of the rectifier topology is required to enhance the DC voltage. You need the combining the RF multiple antenna or multiple rectifier combining DC combining to get the maximum energy, and also the polarization, because the in surrounding environment you have the different type of the polarized wave. So you have to design, you have to consider which type of the antenna can receive the maximum power from the surrounding. And you should know the practical application, how much power the sensor require, because in home and office there are a lot of sensor to charge the. So I think this, I like this smart home using the energy harvesting system. If you design the smart home, because in home you have a lot of space, you can design array or multiple retina and combine, because you have the roof. You can add the lot of retina and combine DC combining, and you have the wall. Everywhere you can put the retina. You have the some very nice design like meta surface or meta material. You can put the wall, and you have the two advantage. You have the design also, and you can get the some power also, and some I think, and DR based meta surface also. If you design wall based on the DR, you can get the energy also. I like this idea, because you can design home, and without electricity you have the uh, power. You can charge your mobile camera, or you have sensor, etc. So because in house you have a lot of space, so for antenna you have a large aperture, you can get the more energy. You can get the energy from every all direction. So if you combine DC combining, or first like you have hybrid DC and RF combining, you will get a lot of power. At least you can uh, charge your low power devices, and one bulb also can light up. And I think the in IIT Silchar, the mobile tower is very close. Taimur can, I think some demo type of the smart home to demonstrate for student other things. So, and this is a very interesting paper, I think recently published, 3D antenna, and they cover 4 band. This paper from Pakistan, they did, I think, step by step. First, they measured the power density around the semi-urban area, university campus, and the GSM tower around the 300 meter from the university campus, and FM tower around 6 point something, some value, I think, kilometer from the university. So they did the frequency spectrum survey, and day night, and 3 4 time, and then they average, and this is the average power available at the campus. So you can see the GSM have the around minus 10 dBm power is outside, outdoor, and they have also measured the indoor. Indoor also is quite high power some. So based on that, they designed the multi-band antenna to get almost all band. and they check the different topology like RF combining and then DC combining, and this the hybrid combining. They use this hybrid combining for three like GSM 900, GSM 800, and Wi-Fi band. They designed the cross dipole type antenna and use the RF combining, and single FM and monopole antenna. They use single band and put the rectifier and combine the DC. And this is the and they designed the antenna as the 3D, and they put the antenna in four different directions to get the uh, wave from all direction. And if you look at the only single antenna, this single antenna power and the outdoor power, they have received output voltage 92 millivolt. If you combine four antenna, and they can increase the power, output power, 123 voltage. And if they add this FM dipole antenna, the power again increase 315 millivolt. So if you have the multiple like this 3D antenna, you put in your house, around the house, or uh, you know, wall or top of the roof or somewhere, you can just hang on, and then you can get the power to charge up some, I think at least some low power sensors. Or this very good idea, very, I think, detail. If you like, I think go through this paper. It's very interesting paper, and they did outdoor and indoor both. I think in indoor, if you have dedicated source, you can get a lot of power because this antenna can receive wave from all directions. So next, these are the some ambient RF energy source surrounding our environment. So you have TB tower, 5G satellite, and mobile tower, RFID reader, handle reader, WiMAX, and Wi-Fi router, hotspot like this. So in environment, we have the different type of waves: horizontal, vertical, tilted wave, the unpolarized. Most of I think unpolarized wave, because if the circular polarized hit some wall or some hit with the metal, the polarization change. If the vertical or horizontal hit some building or somewhere, the polarization wave is changed, and we don't know uh, the device in direction is oriented or tilted or something, or elliptically. There's a different kind of waves in the environment. So main task of the antenna, how to get the maximum energy or different polarized waves, how to capture the different polarized wave by single antenna. This is the antenna. You have to design smartly antenna, can get that almost all type of the waves. If you have the antenna vertical polarized and you don't have the waves in surrounding you vertical polarized, so you will get zero power. So antenna polarization is very important to design the energy harvesting system. So these are the different antenna configurations. This is the just monopole fractal type antenna, very small antenna. And then this one, I think around 600 megahertz for TV band. And this is the wide band circular polarized antenna, monopole type antenna. This is also very small antenna for 500 or 600 TV band. And this is a meta surface antenna, because you know the meta surface can receive the power from large aperture. That's why if you have the uh, place to install the large large aperture size meta surface, you can receive lot of power. And this is the wideband circular polarized antenna, stack antenna, and this is the hybrid DR antenna. Because this one is the below is the patch, and then DR, and then this is the we put the what we call the surface mount to short horn. So this short horn can enhance the around 4 dB gain. So around this antenna have around 9 plus 9 point something gain. So this is the directional antenna can receive more power. And this is the meta surface based circular polarized antenna we designed for 2.4 gigahertz Wi-Fi band to receive the Wi-Fi signals. And this is the dual band antenna with high gain. Due to they have used the reflector like defected or EBG type reflector. And if you have like this antenna, conformal type antenna, you can receive the power from all directions because each antenna have 60-degree beam width. So you can get all around 63 degree, and top one, this one can cover. So this type antenna can be used like a power bank because you have the lot of energy. You can you can charge your mobile if you put the socket. And this is the wideband high gain antenna, and this is the dual polarized antenna. This antenna can receive almost uh, all polarized wave, like this one right hand, left hand, and other polarized wave. This antenna can at least receive the half power, vertical half power, horizontal half power, tilted half power. And this is also very interesting antenna. This is like cross dipole with a six six band dual circular polarized antenna. So this antenna can receive 6 band waves from the environment. And this is very interesting the idea, I think it's proposed by the Rahmasami. And they put hemisphere, they put the 3 type of dipole antenna, right? 3 band and different direction can receive different wave from different direction. And I think both polarized at right horizontal and vertical polarized. And they propose like a power bank. This one can be used like a power bank. So next, these are some other type of antenna like multi-band antenna, dual band fractal antenna, uh, dual band inverted F antenna, dual inverted F antenna. They are the 2 inverted F antennas for dual band. And this is the DR antenna. I think Professor Anta talked a lot about the DR antenna. DR antenna is good, I think, can absorb more power. So this multi-band antenna can cover 4 band, GSM 900, 1800, Wi-Fi 3G also. And these are the efficiency. If you look at this is the DR antenna efficiency, very quite good. So, and for energy harvesting, I think the radiation pattern of antenna is very, very important. If you're using only the monopole type antenna, you can get the energy from the surrounding, but you cannot get from there. This part you will missing. If you have directional antenna, so you can get the only this part and energy, but this part missing. So you have to design smartly wide beam antenna. You can cover at least energy from all directions like this. This is the wide beam antenna plus minus 90 degree or plus minus around 180 degree beam width. This type of pattern can get the energy from all direction. If the energy is very low in the surrounding, then you have to think the 3D type of antenna. You can put the wide beam antenna in 4 direction and one put on the top, you can get the higher energy. And if you know the source, or you have the dedicated source, then just use the high gain antenna. Just align the energy harvesting system and the source. So you will get the power. Next, I will talk about the polarization. Uh, Antenna polarization is very important for communication or for all application. If you know, you have the vertical antenna and the wave is the horizontal polarized, so you cannot receive. So generally the antenna is the linear or circular polarized. So how to design the, like if you want to the receive the two polarized, like dual polarized vertical and horizontal, we have to design the dual polarized. And in the wave in the environment um, surrounding us have the different polarized, linear, circular, elliptical, and unpolarized, tilted, or different type. This is the elliptical polarized. If EX0 only EY, so you have the vertical polarized wave. If EY0 only EX, you have the horizontal polarized wave. If EY and EX is same with 90 degrees difference, you this become a circle. You can generate the circular polarized wave. That there are two type of circular polarized wave. One is right hand and left hand. So if wave is the right hand polarized wave, and your antenna is the left hand circular polarized wave, so you cannot receive, right? So the system is failed. So you have to design the different how to get the different polarized wave antenna, how to get the receive the different polarized wave by the one antenna. So this is the some very this slide is very important to check the how much power you can receive. This is the wave polarization in the free environment around us, and these are the receiving antenna. If you have the dual polarized, horizontal and vertical, at least you can receive full 100% efficiency of um, horizontal polarized and vertical polarized. And other wave, at least you can receive 50% with 3 dB loss. And same in the dual circular polarized antenna. You can get the 100% right hand, left hand circular polarized and other polarized wave like tilted or tilted horizontal, vertical and horizontal. You can get the 50%. If you just design the vertical polarized wave, so you cannot receive the horizontal polarized wave. If your receiving antenna in energy harvesting is vertical or horizontal polarized, you cannot receive the vertical polarized wave. So same in the circular polarized wave. If you have the opposite circular polarized wave, if a wave is the different sense of polarized compared to the receiving antenna, you cannot receive. So you have to match the polarization with uh, wave in the environment. Polarization like polarized, you have to check the, or you can measure also what kind of wave in the surrounding us, majority of the wave, like you have the vertical or horizontal, circular or tilted. So based on that, you can choose your antenna like dual polarized, horizontal polarized, vertical polarized, right hand, left hand, or dual circular polarized. So, as an example of our energy harvesting system, sorry, RFID system, why we use the reader antenna circular polarized? Because tag generally the linear polarized. So tag in any direction, vertical, horizontal, tilted. So if you have the reader antenna horizontal polarized, so only detect the horizontal tag. So this one cannot receive the vertical tag. So to detect the all random type of the tag placement, so you need the circular polarized. This is the one of the I think good example for circular polarized antenna applications. So you can detect the randomly place the tag in the if you go the in library book in any direction, right? Some is the vertical, some horizontal, some tilted. So in library, reader antenna can detect all most of books because the antenna is circular polarized. No matter in which direction or which angle the tag is placed, or your handle reader device in which direction you can move, tilt or something. It's no matter if you have circular polarization in the reader. Okay, next my topic is the circular polarized antenna. How to design the circular polarized antenna? There are the typically three type of feeding techniques to generate the circular polarized antenna in microstrip type antenna. The one is the single feed. You have the single feed. If you have the nearly square patch like L, and you slightly change the this L and feed is diagonally, you can generate the two mode with 90-degree phase difference. So easily you can generate the circular polarized wave. Because circular polarized wave, the condition you should have two mode with 90-degree phase difference and almost approximate equal amplitude. Then you can generate the circular polarized waves. And this is the other example. If you cut the corner, feed orthogonally direction here, you can generate two orthogonal mode with almost equal magnitude. And the other is the dual feed. Feed is very easy. You need a square patch antenna, just feed in two orthogonal direction and 90-degree phase difference. You can receive or can get the circular polarized wave. Other way, you just at the 90-degree phase difference, right? This 90-degree phase difference, you generate this. For this one, you have to have the square patch because you need the almost same amplitude. The other method is the sequentially rotate. So you have the linear polarized antenna. You can rotate like 0, 90, 180, and 270. You can get the circular polarized waves from the linear polarized antenna. For single feed advantage, single feed circular polarized antenna is compact because you need only one feed. If you want to design dual feed, you need extra space to add the phase like this. You need a split divider or adding the phase. For sequentially, you need almost double, four times space. So this is the advantage, disadvantage. The generally single feed is narrow band, typically narrow band, and dual feed you can based on the impedance matching you can get the wider bandwidth, and sequentially also you can get the wide bandwidth. So uh, we have designed number of the circular polarized antenna with uh, single feed and very small size. And this is the our first design using the asymmetric slot. Asymmetric slot in four corners to generate the circular polarized wave. This is very popular paper. I think citation is around 250 because first time we have proposed this idea because we have the smaller, and bigger and biggest. So feeding is here. So you have the two mode, one this side, one this side. If you change slightly the this area, because this area compared to this diagonal line and this diagonal line is slightly the difference in the circular slot. So you can generate the easily circular polarized wave. Then this is the once we have used the slit in the corner, different length width slit, you can get circular polarization. And same in the cross slot, we have asymmetric cross slot. Can generate circular polarized antenna. And other one, because in both way you can generate circular polarized. If like this one is the same areas, same size cross slot, and this is a slightly bigger size like this. Is the same size cross slot in this diagonal direction, and this is the different same size cross slot in this direction. So you can generate circular polarized. And other one interesting, this one, we have used the outside. We bring these circular slot at the corner like a patch. Different radius patch we added around the corner. At the corner, we generate the circular polarized using the single feed. And other one is also very interesting. We use the different length stuff, slightly different length stuff, generate circular polarized. So these two help to design the wide beam circular polarized radiation. And the other one, this is very compact. We use the same concept, but we add the via to create the some left-handed like series capacitance and the inductance can create by the via. Then this type, by using this technology, we can design a very compact antenna. This is also same ring slit in one direction, smaller in another direction. And this is like a toe shape. I will discuss later this I think, in detail. And this one is the again asymmetric slit around the 8 corners. And this one I will discuss. I think next one I will discuss this antenna, how to design this antenna for wide beam circular polarized. So this is the antenna I just discussed. We use the proximity. This is the ground plane. This is the microstrip feed line, and this is the taper slit microstrip radiator. So this is the proximity couple. While EM couple, we can excite the antenna. So the uh, main this design, how to design the taper slit with compact size and circular polarization and wide beam. So if you look at this is the longer slit and then smallest. So like this, we got the idea and we put there, we can generate the circular polarized wave. The the change in this slit length is only the 1.3% from here like this, and then add the 1. Here the This is the largest one, and then this is the smaller 1.3%, like this, adding like this. These are the dimension. We use the Roger 40 RO403, and this is the ground plane area 130 to 130 mm at 900 GSM 900 band. So we have checked the how much size we can reduce. Around 10 to 12% we can reduce. So we created the slit around this corner, and this is the slit width. This corner you can see the without slit, the frequency around 1.04. If you create the slit, we can bring down the frequency 900. You can see here, right, two resonances. This is the two mode, and at the 900, exact 900, you can get the XLSO, like the circular polarized. So these are the some equation how to get the this design. These are the P1, P2, P3 position. You can calculate by using these equations. I think the student did very good job. He designed a lot of equation and get this idea. So this is the electric field distribution. You can see 0 degree, 45 degree, and 90 degree, 135 degree. If you want to check the circular polarization, you just check the how the electric field moving is circularly, or you can see here is moving circularly, right? And this is the current distribution. You can see the current distribution. Majority of the current distribution around the slit, and it's very symmetrically. So if you check the XLSO means you have the ratio of the maxima and minima electric field. So for best XLSO should be 1, means 0 dB. So for practical use, we define the XLSO around 3 dB, should be below 3 dB. So if you look here, the XLSO beam width is around minus 90 to plus 90, more than that. In both XZ and YZ both plane. This is some parametric study. TM is the percentage distance from the center to slit location. If you change this distance, you can tune your frequency, resonance frequency. And we change just to 35.4 to 37.5, not a big range. But if you change in this range, you can see XLSO is still below the 3 dB. The best we can get the 36.4. And this is the gain almost same. We change on resonance based on the change of resonance frequency. The maximum value of gain also shift with the change in the percentage slit length from the center. Next, we have changed the M. M is the percentage change in the slit. Like this is the larger, this is smaller, like this. So M change, M have the effect. If you have the 0.9, you have the frequencies here, and if you have 1.3, your frequency is 900, around 900. And if you look the XLSO with frequency, the lowest XLSO at 1.3. If you increase or decrease, you can see the XL ratio is going to bad this side because it's increasing around 2.5 dB. So this is around zero point 0.5, zero point 0.5 or 0.7. The gain is again not a big effect, only slightly effect with change of percentage change in the slit. This is the D is the upper D is the this one. If you change this, frequency also slightly change, but XL ratio almost same. Is not a big change. So next we have fabricated the optimized antenna and measured. Uh, because this fabrication in-house, student fabricated himself. So we measure, we got very good agreement, almost the same, and this is some difference because the X-ray ratio is very sensitive parameter of the antenna. And gain, this is the gain simulated and measurement comparison. So looks okay. So this is the measurement. You know the circular polarized antenna measurement is different. Like transmitting antenna continuous rotating, and you can see the continuous rotating. This is the radiation pattern. This showing the minima and maxima. The repeal in the pattern showing the maxima and minima. So ratio of this or the minima and maxima difference, it represent the XL ratio value. If you have a very large like this it means your XL ratio around 20. So here is almost like 0.5 or something like this. Here very. So this is the beam width 3 dB. If you consider 3 dB beam width, means this is still in within 3 dB range. This change, this repeal is still within the 3 dB range. So this antenna showing very nice XL ratio beam width around minus or around 180 degree, half sphere. You can see here is all within the 3 dB range. So this one we call the 3 dB XL ratio beam width. So next, we have designed the compact CRL based rectifier to connect the antenna I have presented. So we have used the voltage doubler circuit configuration for design the rectifier, and for impedance matching we have used the CRL, means composite right left-handed transmission line. Means left-handed we use the lumped component, and right-handed we use the microstrip line for designing the matching circuit for rectifier and antenna. And these are the some some parameter of the doubler and input impedance. You can see the 900 impedance is this for one input power for 1 milliwatt and load resistance 50 ohm. And we have designed, fabricated the rectifier. This is the rectifier impedance matching. And this is the lumped component. A student solder all lump component and rectifier, and we connected with the antenna. And this is the rectifier impedance matching. And this one is the measure and simulated comparison of the measure and simulated efficiency with input power TBM. You can see the big difference because this everything we did in the in-house, and I think some resistance capacitance the matching circuit is not good, so we have not get the good agreement, but still we can get the 30% efficiency. So next, I will present the dual band efficient to circular polarized antenna for energy harvesting. So I have presented the GSM 900 band. We use the same antenna in this design, and for Wi-Fi band, we use the different antenna. The motivation to design the antenna operating GSM and Wi-Fi band for energy harvesting system. So this is the antenna, same configuration, a microstrip field, a ground plane microstrip feed line, and this is the GSM antenna, taper slit octagonal patch antenna. And top of this, smartly we put the antenna, this slotted circular patch antenna, and with connected by using the via. So this feed line uh, proximity coupled to this one, and this via can excite this patch. So these are some dimension of this one. We use the Rogers 40403, and this is the circular slotted patch. For Wi-Fi band, we generate the circular polarized based on these slot, smaller and bigger slot based on this, and then feeding is air. And we use the same concept in, I have presented that, and this feeding line. So these are the design equations, how to design these silted or slotted patch. The distance, you can put this value. This is just to cost the scientist in diagonal or other direction. So I just showing some how much is size reduction. So if you don't have any slot in the patch, you have the band here around 2.4. If you cut the slot, you can reduce the frequency. It means you are designing the electrically small antenna. So the frequency is shift down to around 2.4 here. And this the again same thing, around 1.5 frequency to shift down the 900. For because the slit and slot we use for both purpose. One is the size reduction, other one is the to generate the circular polarized. So we have two advantage. So this is the again current distribution same is changing with 0 degree, 45, 90, 135 like this, and 90 becomes 180 becomes same 0. And this is the Wi-Fi band. You can see this one change, and this is 45 and this 90, 135. And this is the video of the field how it's moving circularly. So the field moving in clockwise direction. So out of wave. So this is the left-hand circular polarized. So this is the current distribution in both band, 900 and 2.4 band. You can see the very nice current distribution, very symmetrically. And for Wi-Fi band, current distribution on the Wi-Fi band patch, and then some current distribution also on the GSM band antenna, because GSM band antenna look like a ground plane of the Wi-Fi antenna. That's why some effect here. Okay, so you can see here some effect. If you change percentage change in the slit length from center, the both band effect. The Wi-Fi band is slightly effect, but this one is effect more. It means the Wi-Fi band antenna because changing in the GSM antenna. GSM antenna as a ground plane of the Wi-Fi antenna. So this one have some effect of Wi-Fi antenna. You can look here around 6.25 percentage change in the silage. You can get the very good return loss in here this one, and here somewhere here. So in Excel ratio, you have the minimum Excel ratio at 6.25 m here. And this is the gain in both band. At least we have the more than 5 dB in GSM band and more than 7 dB in Wi-Fi band. And we have also checked the what is the effect of if you rotate this slot, the angle of this slot. This is a theta, angle is the theta. We change theta from 35 to 55. You can see here the GSM band no effect because GSM band is separate. Is below, this is the top. So the only the effect in the Wi-Fi antenna. So at 45, we have the very good performance in terms of the Excel ratio and impedance. And we have also checked this thickness. We vary the thickness and check the performance, and you can see both band is effective, and both GSM and Wi-Fi band, because this height also affect this patch and this patch. So Excel ratio around 6.25 is good here in both band, and this is the gain. And finally, we fabricated this antenna. This look like this, and we measured. You can see the simulated and measured return loss. This is the Excel ratio, and this is the gain. And again, you can see the same performance. It's very wide Excel ratio beamwidth. I think main of these two antenna is wide beamwidth, more than 180 dB Excel ratio bandwidth in at 910 and 911. And you can see here 2.43, the beamwidth is not wide, very narrow, around plus minus 30 or around 60, 70 degree. You can see here. Because this repeal represent the Excel ratio value. If you look here, is more than 10 here, more than 10. So around here is more than 3. So we have to look only the 3 dB. So beamwidth is around 60, around 30, plus minus 30, 60 degree. 3 dB acceleration band, beamwidth for Wi-Fi band. And these are just summary of the major performance of dual band antenna. You can see the return loss, uh, 46 megahertz for GSM and 165 Wi-Fi band. This is the XLSO for GSM band, 3 dB XLSO bandwidth, 12 megahertz and 20 megahertz in Wi-Fi band. The peak gain is major gain is 5.41 is GSM band, 7.93 in Wi-Fi band, operating frequency 920. Now you can see the size is reduced compared to the single band. Single band size is 130 mm by 130. Now is the 120 mm by 120. So this is just some comparison with the other available antenna. Uh, Our antenna is single band and very good gain, more than 5 dB in both band. If you look the other dual feed antenna, this one very complicated and gain value is not so good in both band. This band is very low, but this one is higher. But if you look this antenna, the gain is very low. Same band. Okay, then we have designed the dual band rectifier circuit. Same concept we have used. We have used the CRL based matching circuit, dual band matching circuit, and voltage doubler for rectifier. These are the some parameters of the matching circuit, and this is the voltage doubler input impedance and frequencies 900 this one and 2.45 this one, and this is the return loss of the rectifier at the 0 dBm power input power. This is the prototype antenna and efficiencies. You can see this is the antenna, prototype antenna, and this is the rectifier. CRL, composite right left-handed based matching circuit based rectifier. You can see here with different load with different input power. You can see the efficiency is more than 30% at 0 dBm. And these are the comparison of the measured and simulated calculated efficiency 900 GSM band. And this is the Wi-Fi band. You can see here at least we have around 30% efficiency, 0 dBm measured. So next I will present smart home. We have, if you have the smart home, there are the different kind of sensors. We have the watch and temperature sensor, or air condition, or fan, TV, etc. So how to power up? If you want to power up using the energy harvesting system, so we use the dedicated energy harvesting transmitter, and then this one goes to the butter matrix. You know, the butter matrix can steer the beam in different direction. If you're using 4x4 butter matrix, and butter matrix can generate the beam in 4 different directions. Desired direction is based on the phase change in the. So we use the compact based on the compact crossover and coupler, and this is the crossover. We design very small 4x4 butler matrix to switch the beam in different direction and using the 4 antenna. This is also very small antenna. So I will discuss one by one each element. So first we have designed the coupler or butter matrix. You know the coupler. This is, we use the slotted coupler to reduce the size of the coupler. And the port 1 is the input and port 2 is the isolated, and port 4 and 3 is coupled port 3 dB coupler. You can see here at 2.4 you have the coupling around 3.5, around 0.5 dB loss, and uh, both coupled ports should be 90-degree difference, right? Then you can see here 90-degree phase difference, and the isolated port is I think less than 2. This is the 12, and this is less than 15. We have also fabricated and tested the small, very small coupler. And then we design the crossover for butter matrix. You can see we use the uh, some mandrel line like this to reduce the size. Otherwise, the size is very large. So port 1 import and port 3 is through port. The signal can pass without any change, without zero change any phase. Um, port 2 and 4 is the isolated port. I can see here isolated is still I think less than okay. Through port is the only the loss around minus 0.5 dB, and you can see here around 2.4 and 0 degree phase change. And then we design the butter matrix 4 by 4 butter matrix. You can see here. This is the coupler. This is another coupler. This is the crossover, and this is the coupler. We design and we check the performance. Major performance very good. You can see the little loss is very wideband. And these are the some excitations, different port 1, port 2, port 3, and port 5, port. You can get the and this is the adjusted phase. You can get the this phase with different input at the different feed 1, 2, 3, 4. This is the measurement. You can see the coupled power level are generated are greater than minus 10 dBm. It means see, this should be the 6 dB, right? So there's the 2 dB loss, around 2 dB loss. Mostly loss contributed by coupler and crossover. So for design the beam switching, so we need antenna, right? So we designed the compact E-shape antenna. For in this patch, we created the circular polarization based on the E-shape. This idea came from ESA. So we feed them diagonally here, so you can have the two more. So we use the 403 very small, very low profile 0.8 and length. This one L is 40 mm. Use single feed and E-shape we use to generate the circular polarization and create and reduce the size, overall antenna size. So you can see the electric field distribution again 0 degree, this one, and change the 45 and 90 and 135. Okay, we fabricated and measured, and we have some shift because in-house fabrication, everything, some, I think the dimension or soldering or some material issue. And this is the radiation pattern, both gain, this is the radiation pattern, both axes, X and Y plane. And this is the acceleration plot. And to generate the beam, we need to design the linear array. And one very important point for designing the linear array is the distance should be, interspacing distance should be lambda by 4. If you have the distance between the antenna more than lambda by 4, so you have some grating lobe and other thing, other side lobe or grating lobe issue. So we use the D is very small. You can see the almost, I think, touching the patch. So D is the 36.4. It means in term of lambda around 0.3 lambda. We use to design the linear array for butter matrix. This is the overall system. So these are the 4 input. If you want to change the beam based on the electronically, you just add the switch 1/4. You can switch the beam in different direction electronically. For this project, we just use the manual different feeding and measure. You can see here different port can get the different direction beam. Like 3, if you excite the 3, you can get the beam in this direction minus 60 something. And if you feed 4, you have the beam here. If you feed the 2, you can have beam here. You can have the beam here. And port 1 beam is here. The beam angle depend on the distance t between the element and adjacent phase. So I think I described this phase. Based on this phase, you can get the beam in different direction. So the measured beam direction -5 degrees, 65 degree, 45 degree, and 20 degree when exciting the port 1, 2, 3, and 4. So to demonstrate the wireless system and energy harvesting, we use the tall shape circular polarized antenna. This is very interesting antenna. Student is very smart. He just to think different art of to generate the circular polarized antenna. So he thinks the tall shape can get the very good circular polarized antenna. So this is a very wide band. We use the aperture coupled feed to get the wide bandwidth. So around the 2.4, we use as a rectina this one to demonstrate the beam in different direction. So we just for demo we just put the beam forming system in bathymetric system 1 meter away from the retina energy harvester. So we check where we can get the maximum voltage. So in 3 port 1 at we got the -3 degree angle maximum voltage, and port 2 61, and port 3 -30 53, and port 4 17 degree. And this one I think almost matching with this, and this is the 5 degree, and this is the 3 degree, and the 65 slightly difference but almost same. We have received the maximum based on the maximum voltage. We check the direction, beam direction. Maybe some we cannot get the exact. We just mark the angle and just a student project, so we have not cared fully very precisely for angle. Then we have checked the using the expected power and measured power. You can see expected power this one, and measure power in different input power can follow this graph. This is a very interesting project, but still need to work to get the precisely all angles and etc. This is just a demo for student. So finally, I got I finish my presentation. In conclusion, I have discussed various configurations for RF energy harvesting systems and detailed discuss of the polarization, what kind of polarization is better, or and comparison, some benefit of the if you use the dual polarized antenna or dual circular polarized antenna, you can get almost all polarized wave, but some losses. I have demonstrated also the compact wideband circular polarized antenna at the GSM band, and I have also demonstrated the dual band circular polarized antenna at GSM and Wi-Fi bands for energy harvesting, and also demonstrated the one demo for smart home, how to charge up the sensors using the concept of the energy harvesting and wireless power transfer systems. So thank you very much, and if you have any questions or any query, you can send me the email or you can ask me. Thank you.
Thank you, Dr. Nasimuddin. Thank you very much for your wonderful talk. Would you be comfortable to handle some query of the participant?
Yeah, sure.
Okay.
I like.
Okay, thank you. Now, the first query is, what is the best way of combining power at RF level or at DC level in context of energy harvesting?
Okay, this is very good questions, because it depend. Diode have some disadvantage or some limitation. If you have very low power, you cannot excite the diode. So you need certain power to excite the diode. So if you have power very low, so you should go for RF combining first and use RF combining. If you have high power, then use the DC combining is better.
Okay. The next query is the cutting of slot on a radiating surface is based on some formulation or it is in trial and error?
No, it depends on the square patch. So best is you have to cut the slot around the lambda by 8 location.
Okay.
If you go to my paper, you can get some formula based on the wavelength.
Okay. The next query is the RF energy harvesting system cost effective as compared to solar energy harvesting system?
Oh, very good questions. Because if you go the solar system, you need very large and very expensive.
Okay.
If you have the available power in surrounding you, or you have the dedicated source, I think it's still cheaper and the energy harvesting system.
Okay. Then next is it possible to combine solar energy harvester with RF harvester?
Yes. There in the literature there are some example. Because you can use the transparent antenna using the solar panel. You can combine both. Yes.
Okay. Then, sir, what is the significance of negative gain in dual band antenna? I think somewhere in your presentation you have mentioned that one. I think so.
Oh, okay. Negative gain, because it depends. If you want the wide beam, you have to suffer the gain. If you want the omnidirectional or 3D omnidirectional, you design very small antenna, you will lose the gain, right? So no, it depends on the application.
Okay. Then, sir, last question is how to convert a linearly polarized metasurface based antenna into circularly polarized metasurface based antenna?
How to convert linearly polarized?
Or simply how to convert a linearly polarized antenna into circularly polarized antenna? Would you suggest some methods for that?
You can excite the meta surface using the circular polarized antenna. The meta surface becomes the circular polarized.
Okay, sir. I think all the queries from that participant sites have been resolved.
If you have any question, you can also ask.
Yeah, sure, sure. I'll share your email to them. Okay, to the participant. Later on, they may contact to you directly. Thank you very much. Thank you
No
very much,
problem.
Dr. Simuddin. First for accepting our invitation, then for presenting your quality research in that session. Now, before saying you final bye-bye, I would like to invite you for attending the valedictory session
Sure,
this
sure, no problem.
evening at 9:45 IST, 9:45 p.m. IST. Till then, bye. Thank you. See you again at 9:45.
Okay, thank you so much. Okay, okay, bye.
Now, please,
How to do the?
you stop your presentation, sir.
I have. Okay.
Click on that one from where you start the presentation. Yes, yes. Stop.
Okay, thank you.
Okay. Is the screen visible to all of you?
Yes.
Oh, okay. Now, okay. Now, it is my immense pleasure and gratitude to welcome the second distinguished speaker of fifth and last day session, Dr. M.S. Hashmi, Associate Professor at Nazarbayev University, Kazakhstan. Muhammad S. Hashmi received BTech degree from Aligarh Muslim University, India, and MS degree from Darmstadt University of Technology, Germany, and PhD degree from Cardiff University, Cardiff, UK in 2001, 2004, and 2009, respectively. He had held research and engineering position with the University of Calgary, Canada, Cardiff University, UK, Thales Electronics, Germany, and Philips Technology Center, Germany. He is also associated with IIIT Delhi, India, and was a recipient of Visvesvaraya Young Faculty Research Fellowship under Ministry of Electronics and Information Technology, Government of India. He is currently an associate professor at Nazarbayev University, Kazakhstan. His current research interest includes the design of advanced RF circuit, broadband linear and efficient power amplifier for mobile and satellite application, high and low frequency instrumentation and wireless power transfer systems for low power application. His research activities have led to one book, 3 patent, 1 US patent awarded and 2 pending, and over 185 peer-reviewed journal and conference publications. He was recipient of ARFTG Microwave Measurement Fellowship, and his authored and co-authored papers have won multiple Best Paper awards at leading IEEE conferences. He was the MTT 11 Innovative Design Competition winner at IEEE IMS 2008 held in Atlanta. His team also won the filter design competition held in IEEE IMA 2015 and 2017. Currently, he is an associate editor with IEEE Microwave Magazine. With this, I welcome you and invite you, Professor Hashmi, for this last day, second session, and please start your talk.
Hello, good evening.
Yeah, good evening.
Are you audible?
Yeah, you are audible.
Okay. Thank you, Professor Taimur Khan, for inviting me in this excellent workshop on energy harvesting and power transfer techniques. And it is actually my pleasure to give insights and some information and knowledge about my research activities within the of wireless power transfer techniques. So let me share my Can you see this?
No, sir. Now it is not coming. On bottom right corner, there will be
Okay.
one. Okay, sir.
Is it okay now?
No.
Let me.
So on bottom side, right corner, there is
Yeah,
an.
I know. I can see that.
Okay, okay.
So
On bottom side, right corner, there is.
I can see that. Is it visible now?
Sir, on that same icon, there will be an option of sharing. Share a full screen. Then it will come.
Yes.
Sir, on that same icon, there will be an option of sharing.
Okay. Okay.
Then it will come.
Is it shared now?
Yeah. Now I think it is coming. Yes.
Hello once again, and sorry for this small glitch. It took a couple of minutes to figure out. So I will take you through to some of the recent advances in, especially in low power RF wireless power transfer techniques. And in case if I overrun the time and I do not find or you do not get time to contact me for questions, you can always email me. This mohammad.hashmi@nu.edu.kz. So just to a brief information about the location. I am currently based in Central Asia. It's a huge landlocked country. I believe it's almost 70 or 80% of in area to our country, India, but population wise, its population is less than what we have in Delhi. And you can see this university is a huge university, huge campus, and it's mostly snowing all the time. This is the best time, but unfortunately, we can't go out due to COVID situations. And some touristic attractions in this country that you may want, it's very near to Delhi, and it's roughly 3-4 hours flight from Delhi. So you can see it's full of attractions. So it may not be a bad idea to sometimes visit this land. And before I start my formal talk, I must acknowledge the contributions from my students Kalsin Dotov at Nazarbayev University and Shalin Verma at IIT Delhi. In addition, I am also indebted to my scientific collaborators, Dr. Galimjan Norizbayev and Dr. Nasimuddin from Singapore. A brief outline of today's talk. So initially, I will take you through to some introductory remarks, then fundamentals, and some of the key challenges that we encounter in wireless power transfer techniques. Then I will show you how to design a wireless power transfer technique, just a step-by-step process. Then we will touch through the recent advancements and where is this domain heading, and then some of the interesting observations, insights, and future possibilities that we consider are extremely important for advancing this domain. And then eventually I will conclude my presentation. So what is the premise? Why do we really need wireless power transfer? What is so wrong with existing technique if we have wires and we just get really very good quality of power transfer? Why do we need them? So first thing we have to understand, by this year, it was expected that the electronic portable device, non-portable devices, they will be excess of 30 billion. COVID or no COVID, essentially we are addicted to our portable devices. And on top of that, when 5G, which is almost up and coming, that comes into fray, these devices need to be connected and rather need to be interconnected for optimal information transfer and connectivity. In that context, you might have, most of you have seen many talks, in the past 4 days and even today from the earlier speaker, that energy harvesting has extremely important role. But one thing is, energy harvesting, but how to use them for powering or charging the devices, the gadget. So that's where the role of wireless power transfer comes. See, for example, just a pictorial depiction. Once you have this 5G as a backbone, you will see whether it is biomedical applications, smart card application, RFID applications, hospital, broadband connectivity. You have all sort of possibilities that will come. And all of them, if you see, say for example, if we take just one example, Internet of Things, we hear a lot. There are so many gadgets and devices, they will be connected to each other, even some through hopping, direct connection, hopping connection, and so on. But of course, it is good to have them. But how do you, many of them, if suppose, say, for example, in a very small place, you have so many devices, it's actually unfathomable to even think that we can charge them through wires. It's impossible. So the only alternative that we have is to charge them, power up them through wirelessly. And of course, as you have already seen, this is the typical, energy sources, even in normal telecom environment. Simple. There's only basic telecommunication signal. And you have seen that energy harvesting happens, but now we have to use them and charge them, say, for example, electronic devices. And that's where we will make use of wireless power transfer techniques. So if we get to some fundamental concepts, what is wireless power transfer? In one sentence, actually, if anybody asks, you can always say, okay, it is if we want to transfer electrical energy without the use of any sort of cable medium or wires or any physical hardware connection. And other context is when we have that wireless power transfer realized, then where do we use them? Some of the common applications are implanted medical and portable electronic devices. Say, for example, many a times now you might have heard, or most of us have heard, that e-health, electronic health, digital health, they are going to play a vital role in near future. Say, for example, for cardiac patient, we have pacemaker. There are some, elements that need to be charged inside the body. And that's where, say, for example, if we have a successful high quality WPP wireless power transfer system, we can use this to charge the device directly without, another operation or whatever, and then of course, ever present and ever growing electrical vehicles, say, for example. I just give you an example. It has not become really practical in India per se, but if you visit London, you will find this electric vehicle charging stations at many places. Like it's not like for some extraordinary or very rich people. It is actually for everybody and anybody. So there are already field trials and successful implementations. So these applications do tell us that wireless power transfer is going to stay, and we need to work on this. We have to advance this technique. As I mentioned, wireless link, say, for example, of course, it is air medium is the most common thing. But say, for example, if we have to use wireless power transfer technique for biomedical implants and so on and so forth, then biological tissues also come into picture. And whether it is useful or detrimental, that we will see later. But of course, they become a medium. And of course, they eliminate the need of cables. Many applications that I mentioned, like such as biomedical, portable electronic, electric vehicle, charging, etc., they will get facilitated by this technique. And of course, if you see this, a simple realization of somebody that I will say who did this, a simple demonstration of wireless power transfer technique, it gives an efficiency of 68%. Same setup. But if we use some biological tissue, say for example, here they had this chicken breast, the efficiency went down to 61%. So in the design of such systems, we may have very effective and very good system in air medium, but it tells us, it gives us a clue that the moment biological tissues come into play, they will absorb a lot of energy. So we have to be ready for this challenge. And whenever we design the systems, we have to take these things into context. And by the way, this is actually the one that I am showing. This was done by our friend in Kyushu University in Japan. And so far, this only system demonstration using biological tissue. So you can foresee the challenges. It is not that straightforward. Many people have tried, but still none of us have been able to exceed the 61% limit. So now if we see that, we get down to wireless power transfer techniques, just in broad category. We can have, of course, you see, we hear about, even the title of this talk says near field power transfer. So definitely there should be some counterpart in far field. And yes, indeed, we have that. And how do we distinguish between far field and near field? It has got to do with the wavelength of the electromagnetic signal that is in play. So essentially, if the wavelength is shorter than the power transfer distance, then we call it far field scenario. And if the wavelength is larger than the distance, power transfer distance, then we say it is a near field technique. And usually, the far field technique, there are two very commonly and well-known techniques. They are called, they are based on microwaves, lasers. And in the non-radiative, or we call it alternatively near field technique, we have capacitive coupling and inductive coupling based techniques. Most commonly, there are many, but majorly we can bracket them together in these two categories. So briefly we will go through, and briefly and quickly, just to keep the things in context. Far field wireless power transfer system, the first report was presented by Brown in 1984. And what did he do in far field system? So he has this sort of situation where the EM wave that comes into play, it was microwave. Peripheral circuits, they are called RF circuits, but essentially I should have mentioned that as microwave circuits. So they have to handle microwave frequencies. And you have this transmitting and receiving antenna. For example, in wireless power transfer system, in general, the designers and researchers, they do not care about antenna as antenna element. We think them as circuit element. So that's how we talk. And once this RF circuitry and everything has happened at receiver side, then you need a rectifier for AC to DC conversion. And these rectifiers could be, okay, it's a generic diode based, but nowadays, especially for the earlier speaker, he was mentioning about diode based, and That's more common. But nowadays, power amplifiers are also coming, especially switch mode type power amplifier. In any case, this is not the context of this talk, but just for the sake of completeness, I wanted to mention that. So if you see, what are the major constraints and the challenges and the limitations of this technique? Normally, the size is extremely large, and antenna size plays a role in that, and usually it's large. And efficiency is extremely poor due to path loss and poor antenna gain at these high frequencies. It is practical, but actually it is actually not useful for low power sensor nodes and biomedical implants. So that's why we will not talk about this further. But it is imperative to mention that it is an extremely good candidate for space applications. So now, let's come into this near field wireless power transfer system. So the first thing is inductive power transfer. And needless to say, we all know this Faraday's electromagnetic induction. So that comes into play here. And if we see this simple block diagram, so you can see this. We have primary and secondary coils. So primary is excited. So it transfers power. There will be a magnetic field generation in the secondary coil, and then you will have accordingly power transfer. So this concept is called magnetically coupled. So it is based on a similar concept to what we have in transformers, in electrical high power systems. So its working principle, as I mentioned, this is based on electromagnetic induction. And again, diode rectifier converts AC into DC. And as I mentioned, near field is here. It is going to stay. It is up to the researchers to make it useful and beneficial by making the advancements. But it has extremely important role in biomedical and electric vehicle type applications. The second category in near field system is the capacitive equivalent. And as we know that the moment capacitive thing is here, it's based on electric field concept. So the working is, you have two parallel metal plates. They produce displacement current, and those displacement current, they will allow transfer of energy from one plate to another. Again, you need a rectifier. It doesn't matter whether you have diode based or power amplifier based. Indeed, you need a rectifier to convert AC into DC. And it has actually come out well. It's in real applications, especially in electric vehicle charging. Even some of the smart cards systems, they use this. And IoT sensor, it has potential. As per my knowledge, I haven't seen any realized system for IoT applications yet, but I am positive that this will come soon. The third, that is also a very, very important concept in near field system, is magnetic resonance power transfer. Essentially, it is similar to inductive power transfer, but the challenge with inductive power transfer is the power transfer distance is very, very low, very small, and the range of power, like the magnitude that is transferred in inductive power transfer, is small. In magnetic resonance, the idea is to enhance both the transmission range as well as the magnitude of power transfer. And you can see, and why it is called resonance. And you can see this. You have L and C in both the primaries and secondary, and so they create a sort of resonance condition. And band stop characteristic changes to band pass characteristic, transfer the power at resonance. And you see, one of the primary is transmitter, secondary is receiver, RX we call, and it is nothing but we can say that it is in continuation of inductive power transfer. So essentially, magnetic resonance power transfer is an advanced version of inductive power transfer. And it has potential for biomedical, RFID, smart card, IoT, and myriad of applications. So now, say for example, in summary, if you see, it is just for the sake of completeness. So we have inductive coupling base, resonance inductive coupling base, capacitive coupling, RF and microwave type, and light waves. So you can see the inductive coupling has very short range, like the power transfer distance is very small. Resonant inductive is mid-range, so it is good for biomedical type applications. Capacitive coupling is short, but it's actually somehow I see that it is in use in electric vehicle type application. RF and microwave and light waves, lasers, they are in gigahertz and terahertz range. They are for this application. But you can see that they have, all of them have certain applications earmarked and they can facilitate this. So it means we have to really see the advancements in this technique. The other aspect that I wanted to bring to the notice of the audience is, it's not always hunky-dory. There are key challenges we have whenever we, as with any other electronic system design, we face many challenges, and it's no different. And the four key challenges that I could find with RF transfer power transfer techniques are misalignment between the receiver and transmitter. Ideally, we want them to be in exact line of sight, but it's not always the case. In real applications, we may not achieve that scenario. So misalignment is one of the challenges, and it will be clear soon through pictorial depiction. I will show you what it is. Then the power transfer distance, separation distance, if it is of the order of at least 1 centimeter or more, then they are really useful. Then impedance matching is another challenge, and you will see what is that. And of course, circuit size, especially you see the context. If, for example, if you want a wireless power receiver tagged to a biomedical implant, definitely we want that receiver to be extremely small. We don't want it to be big, since anything we put inside the body, it has to be of nature size. So let's see one by one. What do I mean by misalignment? You see that there are two coils, they are facing each other, right? So if they are in perfect alignment, it means they are exactly on top of each other, separated by a distance, whatever a distance that you want for the power transfer to work. So, and then there could be two types of misalignment. One will be, say, for example, if they are laterally misaligned, either in X direction or Y direction. Another could be angular misalignment. If we just misalign them by 20, 30, 50 degrees. So these are the challenges, and they will happen in real life. And what happens? Say, for example, we accept that the misalignment will happen. Then what is the repercussion? One thing will be efficiency will drop significantly. And in order to overcome, there has been some solutions where they have this switches and array of capacitors to overcome them. So this detail one can find in this transaction from 2004, authored by this Korean group. The other thing is, second challenge is, power transmission range, and that is essentially the separation distance, the distance between the transmitter and receiver. Ideally, what do we want? We want the transmitter and receiver to be in a strong coupling condition. But if we take them far away, the coupling will become weak. At the moment we have weaker coupling, our efficiency will drop down. The ideal scenario is we have to keep them in a strong coupling condition. It means in general they have to be close. For example, if you see this, P1 is transmitter side and P2 is on the top is the receiver side. And there you see the H is the separation distance. So any design that we do, they are limited by this H. We cannot take them too far. That is the challenge. We as designer, innovator, we have to propose some approach how to increase this power transmission distance or separation between the transmitter and receiver. And in general, if you see this top class paper from our friend in Japan, so they developed one, and reported one, WP system for near field application. It had a very high efficiency of 85%, but the separation was only 5 millimeter. The moment you take it to 8 or 10 or 12 millimeter, the efficiency dropped drastically. But the problem is there is a trade-off now. So whether we really want a poorly efficient system, definitely no. But do we not want this H to be large? Definitely yes. So it clearly says there is a trade-off, and we have to keep this in perspective. Other challenge is matching. Okay, now say for example we have transmitter and receiver. Transmitter is getting power from somewhere. We have to make sure that maximum power from the source is transferred, is sent to the transmitter, so that it will transfer the maximum available power. Therefore, in this figure, you can see there are techniques to create some matching scenarios. And we all know that impedance matching creates that environment where we transfer power, maximum power from one end to the other end. Challenges are, of course, we can create impedance matching networks, but it doesn't come for free, it comes for a cost. And the cost here is creates complexity in the wireless power transfer system, and the robustness of the overall system deteriorates. So reduces, the robustness reduces, and we do not want that to happen. Again, this aspect was reported by Heckel and our friend from Kyushu, that is Professor Ramesh Pokharel. They are very active in this domain, and it was reported in 2016 or 17, TMTT, Transaction on Microwave Technique. Many details are there in the paper. Due to paucity of time, it cannot be explained. Now, of course, as I mentioned, another challenge, and actually it is extremely important, that is the size. The size is actually something that has to be always looked into, especially for low power applications. This, you can see this power transfer setup was reported a few years back by a group in Canada. So they developed this system at 13 gigahertz, 13.56 megahertz UHF type with extremely high Q factor. But one thing that I would like to mention, high Q factor is actually very important even for any frequency. Say for example, when I will be talking about more advancements at few hundred megahertz, Q factor has to be very, very high. The moment we have high Q factor, it means we are talking about the narrow band. And narrow band leads to all the power concentrated in that range. And that also aids in high power transfer. So remember, keep that in mind. I may, due to oversight, not mention this aspect again during the talk, but always remember, for a successful and very high quality wireless power transfer system, the Q factor of the transmitter or receiver should be extremely high. Q factor is inversely proportional to the bandwidth. So bandwidth, the moment we have high Q factor, the bandwidth will be small, very narrow, notch type, and that's the requirement of, in general, a wireless power transfer. I'll tell you a new trend where we also need broadband, so that is later. So, but in this case, what happened? You can always increase the quality factor by introducing parallel strips on the bottom plane. Essentially, we have to minimize the bandwidth. But the major challenge is the size that the researchers reported was actually huge for low power applications. So it's not really practically useful. So say, for example, if we want to use this concept, we have to really put a lot of effort to miniaturize this. So we saw these 4 challenges, and here they are brief. I think due to paucity of time, let me move ahead. It's there in the talk, and if needed, I can share the presentation slides as well. So let's zero in on the near field inductive coupling type wireless power transfer system. In general, if you see, I already mentioned there are 2 types. It's the pure inductive type, and the other is resonant coupling type. On the left side, you can see inductive coupling type, just simply 2 coils, and that's it, primary and secondary. One can work as transmitter, another as receiver. In resonant coupling, you also need capacitive element, and for that, you have these loops. And in general, there are multifarious types of inductive system or inductive resonant coupling type, and the configurations are based around defective ground structure. Especially, I'm sure that the audience here, they have heard a lot about slot and defective ground and EBG type thing. So I will just tell you that in circuit design also this is extremely useful. Then there are also printed coils type configurations, lips wire configurations, copper tube type. But I will focus on defective ground structure type configurations from now on. So if you see this, this is a transparent type. You know, on the left you can see this typical depiction of DGS structure. So you can see the top plane is just a microstrip feed line. So they are just for, you know, connecting sort of thing. So the top plane, when you have this, you have to take any substrate. You have bottom copper and the top copper. In the top, you will etch everything. Just you will keep the microstrip line as a feed. Then on the bottom, you keep all the metal, the copper. Only you cut the, say for example, here it is square loops on 2 sides, like 2 square loops. And you can see in those loops there are slots as well. So they will help us in achieving the resonance. When we talk about this equivalent circuit of this, I'll show you. And of course, square loops, they will give rise to inductance. The reason currents are flowing there now. And you can see those slots, etched slot, they are very interesting. We can also call them gaps in the loop. So they create a small, very tiny capacitive environment. So say for example, if that capacitor is not enough to create resonance of our liking, of course it will create resonance, but those frequencies may not be sufficiently useful. Then we have opportunity to load those slots by external capacitors, and that is the usual practice. And those external capacitors will dictate the resonance that we want. And let's see just quickly the type in general. You know, there are many types of defective ground structures, especially in the context of wireless power transfer. You can see, you know, the first one is dumbbell shape, and I will show you actually these in general. For a broad as a simple statement, these shapes really have less role to play than actual the design skills and the design techniques. Then you see this B is triangular head dumbbell, a square head dumbbell, a spiral BGS, the D1, the D, then E is the meander lines, the U slot, Then you can see the square open loop. These are very commonly used DGS structures. So DGS, just to reiterate, basically you cut these type of shapes in the ground plane. Now, say for example, as I mentioned, we make use of these structures as a circuit element in the design of circuits. So once we have these DGS, it is imperative, it is pertinent to understand that we have to develop equivalent circuit of these DGS structures. And there are two very commonly used techniques. One is called curve fitting, of EM simulated S parameter. EM simulated S parameter, what is that? When, say for example, if we take this type of DGS shapes, we do this in structural simulators. Say for example, CST or HFSS, they are very popular software tools. We prefer CST, but HFSS is equally good. So say for example, the simulation results that we get, they are called EM simulated, electromagnetic simulated S parameter. Then we take this, we bring it to circuit design tool, say for example, advanced design system from Keysight or Microwave Studio from AWR. So we use them and we try to develop equivalent circuit. The other equally interesting technique is quasi-static modeling. Here we do not make use of those S parameters, rather than we intuitively develop circuit model based on the dimensions, physical dimensions of the DGS structure. But typically they will look like this. At the DGS unit, you can see in the red dotted block, the LRC parallel circuit. Usually you see L is due to the loop and R is, okay, now the loop is made up of metal. So R is the metal may be lossy. In general, in transmission line circuit designs, we always consider that we have a lossless circuit. So we ignore R, and that's what we will do in subsequent slides as well. But this is a complete picture, and C is due to those gaps. Capacitance with if we load additional capacitors, then it will be parallel combination of this gap capacitance and the external capacitance. So this is the equivalent circuit. So now we have almost seen the overall background of this talk. Now I'll go quickly into the advancement. And yes, before, so this was, say for example, this DGS unit in the red block, it is for one of the coils or DGS unit. So basically that is transmitter side. If we want to make use of and develop this into wireless power transfer, then there will be receiver side as well. So you will have two of this in coupling, magnetic coupling situation. So that's what we have. Wireless power equivalent circuit, we will see later when we come in the advancement, is just for the sake of completeness. I have shown that you have, say for example, TX is transmitter, RX is receiver. So you have transmitter side, the bottom is the DGS contribution, the circuit. And the right side, receiver part has the lower part for receiver. And on top of that, the CST and CLS, those are for achieving the matching scenario. We will see how it is done. So now we see that any DGS-based circuit can be transformed or at least visualized in the form of equivalent circuit. And almost every circuit designers are familiar with this. They do struggle with antenna concept, but you talk to them about circuit, then it makes them really confident. So let's see, say for example, even before going into the advancements, say for example, first question that comes to us, how to start the design? How do we do that? So I was able to publish one recent paper in IIT Microwaves Antenna and Propagation with my Indian students, and it is available online. So this next few slides are coming from there, like how to do that, how to design this DGS based WPT. So the first step is choose a defect shape for resonator. And okay, the first statement is how do we choose it? Which shape to choose? So ideally, you can take any shape. I will tell you towards the fag end of this talk that shape really is not a big contributor. But say, okay, you are for you like circular shape, or say for any shape. So take that shape. Okay, and then of course, the first step is to develop a resonator. So resonator size, that if we are talking, say for example, transmitter or receiver, if we talk just about transmitter, then just a standalone, then that is a resonator. When we couple them together, then they become wireless power transfer system in general. Otherwise, a standalone, they are resonators, a two-port circuit. Then, say for example, as I mentioned, you can choose any shape you like. This triangular, rectangular, a square, you name any, and so many dumbbell shapes. Say for example, I chose this, all of them. And then if you just run a simple CST simulation or HFSS simulation, you will find the S21, that's essentially, that gives you the power, like, S21 modulo square is the real power transfer. Yes. So in this context, if you see this S21 from one port to another, then you can see the resonance that you achieve. They are distinct for triangle, rectangle, square. So now, depending on your requirement, you can choose whatever frequency you want. Say, for example, if we have to design a WPT system around, say, for example, 275 megahertz, then definitely this 0.3, that is 300 megahertz, is closer to that. So let's take that triangle DGS for that application, for that matter. So then, once we have that, we are ready to move to next step. So first thing is you choose a defect shape now. Say for example, we chose this triangular shape with a slot, slot as well, a gap, and you can see this height is h, base is b, and then overall these dimensions are there. So you look through many things. Say for example, I wanted to design at 300 megahertz. How do we identify? We just try to go and see this surface current distribution, and if it is really good at at the edges, then we say yes, it somehow fulfills our requirement. And if we have to do some fine tuning, we can do this. The CP is there in the slot, so we can manipulate that, we can vary that. Since this is additional on top of that, whatever gap capacitance you have, this is CP is external capacitance, and that is in our hand. As a designer, we have full control on its choice, depending, of course, on the availability and standard in the market. Once we are done, what do? We develop the equivalent circuit of this. And you can use any circuit, high frequency circuit simulator, and usually ADS or AWR, they are good simulators. And you can see, as I mentioned, so usually in these transmission line circuits or like substrates, we assume that it's a lossless or very, very small loss happens. Loss tangent is very small. So we ignore the effect of R, the resistance that comes due to metal. The reason we have seen, observed it, identified that the role in general at these frequencies around 300, 400, 500 megahertz range of frequencies, these losses are not significant. Once we have developed this equivalent circuit, now is the time to compare the circuit performance with the electromagnetic simulation performance. So you see that somehow, of course, by the way, this is the final results that we have. We had to do a lot of iterations. And you can see this circuit simulation S21 and circuit simulation S11. That is good enough for two-port circuit. And the structural simulation, that EM simulation that we get from CST, they are in perfect agreement now. You get excellent agreement between these two. It means now our resonator is actually very good. We wanted to design at 300 megahertz. We got exact 300 megahertz resonance frequency, at least in simulation. So, and as I mentioned, it's not that you achieve this in one go. It takes multiple iterations. And generally, if you ask as a student, if we go to class, they usually ask, Professor, what are the usual things that we need to change to optimize this and to do the iterations? Normally, in this sort of example, there are few parameters that you can see. The height and width of the triangular defect, the dimension of the gap, and that's funnel shaped gap, and the additional external capacitor CP. So these are the things that you can play with. And usually with experience, you also know how to move about. Definitely, in one go, it will be really, actually, you will be lucky to get it in one go. Normally, it takes a lot of practice. Now, once we have validated the resonator performance, what do? We want to develop a WPT system now. And then we will simulate it. We will develop equivalent circuit and then validate it. That's what we will do. So you can see now the top is the transmitter. So one of the triangular shaped DGS, and the bottom is another triangular shaped DGS. And they are in back to back. Both the things will be, in front of each other. And then we develop the equivalent circuit. So you can clearly see the bottom part, LP, CP, this shunt circuit, both are, you see, there is coupling also, K. Now you can see clearly how it is that, right? And all other aspects, they are like, they were done using couple line impedance matching. So they are those things, they are not important right now. So think about these coupling and the two equivalent circuits representing the transmitter and receiver. And once we simulated them, you see, in one go, we could not achieve that. You see, resonator was perfectly all right, but the performance of the WPT, they are shifted. And even it's not a fabricated prototype. It is just in simulation itself, you see the variations. You can see many other aspects have come into play, the matching. The misalignment come into play of this receiver and transmitter. So you have to do again multiple iterations to achieve that. And of course, as I mentioned, you can see the anomalous behavior between the circuit simulation and EM simulation from CST and ADS. And of course, you can overcome. You have this control on capacitors, the gap capacitance, and all so on and so forth. So we have to handle them. Really. Once we are ready with, okay, we optimize the circuit and we optimize this design, the next step is to develop a prototype. So this prototype is only for one of the resonators, by the way. It's just one. But in the instrumental setup, we have both the ports. So two. So you can see, again, we have some anomaly in the measurement and EM simulated result. That's okay. That is well accepted in normal scenarios. But if we want better, we can always go back, develop another prototype and redo that. And if we want to find the efficiency of this wireless power transfer system, then it's usual. It's from the standard any microwave engineering book. Say, for example, Pozar or Collins. We can use them. And these formulations, S21 modulo square upon 1 minus S11 square, the return loss. And that is also transfer power over 1 minus. In this scenario, we were able to achieve 80%. And actually, why we didn't want to go back and redo this 80% efficiency itself is very high for any realized system for single band. At that time, it was. So now, other things that we can do, as I mentioned, that other key challenges are the misalignment. So you can see now, we misaligned them. The top one is misalignment in X direction. The bottom is misalignment in Y direction. And then we did the same experiments that we did for, in this slide, it was just for one distance of, say, for example, 17 or 18 millimeter. And here we did that now. Say, for example, you can see the efficiency drops in both simulation as well as in measurement. You see, and after 20 millimeter, there is nothing that you can achieve. The reason is simple. The transmitter and receiver, they do not couple with each other. So that's how it is. So we know that there is a critical optimal distance that we can do. And we also did this in Y direction. Again, same challenge, same problem. And that was expected anyway. If they don't overlap with each other, how do you expect them to be, transferring power? And of course, then there are challenges. But again, we have to be privy to the fact that these challenges are going to stay, but we have to create better system. The other thing could be, angular misalignment. You see, now both the transmitter and receiver are there, receiver on the bottom, transmitter on the top, and we can do that in 360 degree. Instead of doing this lateral, we do this in angular fashion, misalignment. And then see, usually this sort of behavior we got, and that was expected. You see, the moment they are angularly misaligned by 180 degree, or 150, 160, 170, 180, in that region, the power transfer is expected to be low, and then efficiency will be smaller. But otherwise, if it is close to 0 degree, and then again 360 is similar to 0, it's just the orientation has changed, and you get very high and better performance. So that's how we have to make sure that we don't really misalign them angularly 180 degree under any condition, even in practical systems. So now coming to the major part, but I hope that gave us a clue that how the system is designed, and how and now advancement should be straightforward. Like how then I will run you through some of the recent developments. But you see, even advancements are two-pronged or dual-pronged, we say. One could be, say, for example, if we have a single band wireless power system, WPT system, then we have to improve its efficiency, power transmission range, size. Of course, and why do we need size? Size, it facilitates compactness. That's extremely important. And power transmission range is actually contributes to, it will actually be, useful for practical applications. So, and of course, we have to make sure that we achieve size miniaturization and power transmission range enhancement while keeping the efficiency high. Otherwise, it makes no sense. And then the second direction that is attracting the researchers is making this wireless power transfer system useful for multi-band wireless power transfer. Say for the 12-band, tri-band, say just one system we have, and we are able to charge many electronic devices operating at different frequencies. And the second aspect that we have identified, still I think there are lots of observations and investigations needs to be done. But say for example, we want, say for example, in digital health, we just do not want to charge the, the pacemaker electronic system, right? Say for example, we want to get the real-time information from about the pacemaker, then we need to transfer and receive information as well. So we can say that for simultaneous wireless and information power transfer, these sort of multi-band WPT could be extremely useful. And I'm not talking about half duplex. It has to be full duplex transmission. So in that case, we need at least 3-band or more. So if we see this advancements, one aspect, let's see this. I will just talk about one paper each on these topics, so that in order to keep the interest of the audience, otherwise it will become monotonous. So let's take this paper that we talked about earlier, a novel technique for compact size wireless power transfer applications using defected ground structure. So defected ground, DGS is also used for, like, actually it's a very interesting observation. It's even not only in WPT, it's used in variety of applications for miniaturization of circuits and its components. So in that paper that I just mentioned, they use this H-type DGS. So why they said H-type? You can see this on two sides. They are the two edges of the H, and this slot that they cut, they touch both the end of these slots, these defects. So they call it, looks like H-type. And the equivalent circuit you can see now, it has two parts of this L and C shunt parts. Since you have two edges, and the equivalent circuit again you can see L and C. These are equivalent. Usually we can ignore the reason that its impact is very small on WPT system. This L and R I already mentioned, and CP that you see here, it's the gap capacitance that you see here in G gap, and the external capacitor that is loaded, CLP, you can see this blue color. So that's what it is, external capacitor. So they are in parallel, and so they are combined CG plus CLP. That is the CP, the total capacitance. And now, so that was the resonator that we have. And if we take its performance, both in a structure, in CSP, as well as in ADS, circuit simulation, you can see they reported they are in very good agreement, and they concur with each other. There is slight variation, a small variation. They could be, as I mentioned, due to, there are always, when we do this circuit simulation, we do not take into account the substrate parameters, especially, and so they also contribute to this anomaly. But overall, they are good. But if you are not satisfied with this result, you can always take this, go back to CST simulation or HFSS simulation, do the necessary modification, and then come back. And hopefully you will achieve. Or probably they were able to do this within, since time is finite. So within finite time, that's what they were able to achieve. And it's actually a good parameter. So now when we do this WPT, we have to use, see, this bottom layer is the H. So we have to use two together. And then you can do this analysis, and eventually this will be the circuit that we have. The eventual equivalent circuit for this H-shaped resonator. And they developed this design. And why was they doing this? This is for creating a smaller circuit. And you can see they are actually very, very small. They were on a size of 21 cross 21 millimeter square. So they are actually very small, very compact. And they evaluated the performance. You can see measured, EM simulated, circuit simulated. They follow each other. And a slight variation will always be there. As designers, we know this. And you can see the special features of this design. Why I say it really, it was a significant research outcome. You see the size at the time, 2.5 years ago, 3 years ago, it was actually very, very small, 21 cross 21 millimeter square. And it was done at a relatively higher frequency of 300 megahertz. And efficiency that they achieved was 68%. The first trial I showed you, it was just 5 millimeter. Now they were able to do this for a distance of 13 millimeter. This much efficiency. It was significant work at the time. Then this S. Chalice and all, they reported the practical demonstration of one WPT system. We know that, usually what happens in WPT system, the major, challenge is to, our wish list is to design highly efficient WPT system. But the problem is efficiency requires very strong coupling, K, that you can see here, K. But the other requirement is the Q factor should be extremely high. Remember, I mentioned that we need narrow band notch type performance, and bandwidth is inversely proportional to Q. So now you see this K and Q, they are antithesis to each other. If we change one, make it, try to satisfy one, the others will go haywire. So And as just for completeness, K is inversely proportional to inductance and Q is directly proportional. So what the researchers did, they did one thing. They defined one parameter in the design, U factor they call, and they call it K times Q. And they tried to optimize this, and they actually achieved very good performance. And this is so far the only system with biological tissues. And it is remarkable for a distance of 50 millimeter and efficiency of 61%. Yeah, the only, the cons is its size was large. So far, I haven't seen people exploring, even our research, we haven't explored biological tissues yet, but we do intend to do that in future. Then the other thing is, advancement in single band design was efficiency and range enhancement. So it was done by, again, my student. And it was presented in Bombay last year in December. And in this, the overall goal was to achieve both efficiency as well as range. We can afford to slightly forego the size. So say, for example, we chose this plus shape. Just as I mentioned, effectively, shape will not matter really. But let's see that, okay, we chose plus shape. And in that, we just in order to, before going to fabrication and prototype development, we just chose two, sizes of this board size and separation distance of 20 millimeter. Just we chose. And we compared the performance. You see, for a smaller size, you can see everything is same, no problem. But effectively, if you want, but one thing is, you can see, the moment you start increasing H, you see this 30 millimeter, that and the smaller one, 20 cross 20, showed, very, very small efficiency as compared to the other one. So that's why we chose, even with, if we lose some board area and we can achieve higher efficiency, then why not? So we chose the second one. The reason, in any case, if we wanted to do more, like, the board size increases and, the range is smaller. So we chose the other one. And somehow, and then we optimized the performance. And you can see this plus shape, there are these optimized dimensions. And then we went ahead and developed this equivalent circuit. As usual that I showed you, so it should be quick. And then we did this, this CST and ADS comparison. They were in exact, perfect agreement. But again, I tell you honestly, it was not achieved in one go. It took several iterations. And efficiency was achieved at 86% at 25 millimeter. And efficiency calculation was done using this formula, standard, well-known formula. Then we developed this. This is a simple resonator, but of course we use that in the development of WPT system. And then we achieved this measurement result. And in measurement, we got around 80%. And so it is not far off from the simulation. Effectively, it was good. And for a distance of 25 millimeter, we were able to enhance the range and at the same time kept the efficiency high. Of course, we lost something on the size. But then there is another figure of merit that relates size and for trade-off, size and efficiency. Figure of merit is efficiency times range divided by a square root of resonator size. So everything now, all three came into picture. And if we do this and we do this a quick state of the art survey, then you can see that depending on the need and depending on the applications, you have different shapes. And this plus shape that we reported, it was able to enhance the figure of merit, even though it was larger in size, but it was able to convey that of course it is advancement. And you can see there are plenty of designs and they have improved over time. So now the second aspect was multiband. As I mentioned, you may need, to charge, devices operating at multiple frequencies. So you want multiband operations. So, and the simplest of multiband WPT is the dual band WPT. So the first one was dual band was reported in transaction uncircuit system, and it was again from the Japanese group. They developed a circular shaped DGS based WPT. So this was this is this resonator, and a simple WPT structure will look like this. And they just showed that they do work well, and you can see the ADS and HFSS performance, they are in good agreement. Then they also developed this in hardware, and they showed that this achieves a very good performance. Board size is also not that large, and frequencies of 300 and 700 megahertz. Efficiencies were good at both the bands, but the distance was limited to 16 millimeter. But okay, that was a good try in one go. In the similar vein, we reported last year one of the results that we got in hexagonal shape. We developed this, of course, as a resonator. This two hexagonal, they are dual band, one for one band, another for another band. So dual band resonator. Then we developed resonator circuit, and then we came to develop this full WPT circuit that we are showing here. And then we developed the prototype, and we measured, and we were able to report that the distance we could improve by few millimeter, and the efficiency also in second band was better. And it is more logical for ISM band applications. Say, for example, 400 megahertz, and this is 900 mobile GSM applications. So this was very good. So now, in that similar vein, I will just go through quickly about this double square shaped WPT. So it's also, you can see this, we have two cuts, two DGS, two defects in the ground. So you have apparently you can see that it will give you dual band performance. So and we did it for 30 megahertz and 900 megahertz. Again, the ISM frequencies. It was done in last December in Singapore. Then we developed the equivalent circuit of this resonator. Of course, you have one of the bands, then second band, LP2, CP2, and we developed this. And we did the CST and ADS simulation. They were in good agreement. So we thought, okay, it is good. So let's develop the equivalent circuit of this WPT, dual band WPT. No challenge, no problem. It all went well. But we found that even though the resonator was working well, but EM simulation and circuit simulation results didn't match when we did, this WPT. So we had to restructure this one. This was the original circuit, and you can see the restructured double square shaped based resonator. We did this change in that top plane as well. You can see this open in the right one, and this open stub we are using. And then you can also see this feed locations, the gap locations. You can see we changed them. You see one of them, the CP1, this is in the edge, and even this somehow we had to rejig multiple iterations for these excitations, and only then we were able to. I'll show you that it really achieved the result that we wanted. You can see simulation results. They are now in even more better agreement for these resonators, and then we see that the efficiency for WPT, it was 90% for 400 megahertz and 88% for 900 megahertz, and they are really good. So now it was time to do this prototype development and the experimental setup. You can see we developed this D was 15 millimeter, and the Rogers prototype was done on Rogers board, and effectively you can see this experimental result, and from there we calculated the efficiencies of 71% and 81%. Of course, we never achieve exactly what we achieve in simulation, since there are many human error, there are fabrication errors, there are losses that we do not account in connector losses, etc. We don't account in simulation, but in practical realization you do encounter them. So they always worsen your performance, but still it was very good. And figure of merit, again, as I said, it relates all the three aspects. So that gives you a very good performance of 0.84 and 0.96 at two different frequencies. And if we see this existing many things, then you will see that these advancements have happened over time. there are ways to go, but still you can see figure of merit that we reported only a few months back. They were, you know, advancing the state of the art. Size is also good with this figure of merit. So we say that it is, of course, it has advanced the state of the art. Then just as I mentioned in multiband, the other thing could be this tri-band. So since I am not, you know, discussing this a lot, just only thing I tell you, this is a very niche research direction. And this in communication domain, researchers, they always talk about simultaneous wireless information and power transfer, but we do not see the circuits yet. So this domain of this tri-band and more wireless power transfer could be a game changer in swiped. So and what we have achieved, figure of merit of course for tri-band it's good 0.5, since nobody has reported. So whatever we got, we tried to get, this is the best that we could find, and it was good. It is in review. So I just move on to next stuff. That is the final thing that I wanted to give the audience some insights on the design. As I kept mentioning that shapes in general, they do not play a role, big role. They do play, but it is not that significant that people say, okay, let's take this shape or that shape. Actually, more than the shape, it is the design technique and the skill of the designer that is more important. So let's see if we take these 6 shapes: circle, ellipse, H, plus, square, T. Same board size for same transmission distance and same this defect area. Like if we cut, say, for a H, similar type of area we also cut for circle, so that in order to make keep the proportion same. So what we found, this one can find a detailed thing in our recent paper in May that we authored in collaboration with Dr. Nasimuddin and the earlier speaker, and we were able to identify that in general H shape was not really good for overall design, but it did advance the technique. But the other shapes, you can see whether it is the black bars or the red bars. The black bars are without optimization. It is just you cut the edge, those defects, and you just simulate. Keep the proportions of cut for all the shapes same, and then you find that more or less there is not much difference. But if you want to optimize using external capacitor, we could see that more or less, okay, this one, the circle gave the best, but others were not far behind, except you can see this red bar, except the H shape. All others remained in more or less good, this thing. So what we found, that we should not focus too much on shape. There has to be something else to design that. And as I run through some of the recent advances, you can see researchers did, okay, they changed the slot location and so on and so forth. And so those are more important than the shape. The other aspect that I wanted to bring, you see, we always use different types of substrates, different thickness. So we did, my student run through some of the simulations that I wanted to share. Say, for example, now, if we go to simple Rogers Corporation website, you will find, substrates in different thickness. So you see, usually he did it for 3 different thicknesses of 70 micrometer, 35 micrometer, 18 micrometer. But if you are able to play with the capacitance, the external capacitance that is in your control, the performance will be almost similar. It doesn't matter how thick is your board, like the thickness of the substrate. So it doesn't really matter. Similar defect size, when we did it, it has huge impact. So you can see this bandwidth will change significantly. And if your bandwidth changes, like for large bandwidth, if your power is distributed there, the efficiency will be very, very bad. So you have to take care that whenever you design a WPT system, the defect size has to remain small if you want highly efficient WPT. Then if you have this substrate thickness, again, it also has a huge impact. So that was a copper thickness. that the top you have copper, on the bottom you have copper. So those thickness were not that relevant. But if you take this, glass epoxy or something in between that dielectric, so that is extremely very, very important. Its thickness plays a big role. You can see this bandwidth changes. You see this blue dotted line, plot, and red dotted, and this solid line. So they are like having different bandwidth. So they play a big role in the overall performance. Similarly, if we go for different dielectric constant, you see there are 2.2, 2.5, 4.3, 8, or even alumina has 10. So you do this, usually dielectric constant didn't show that much impact on the overall performance of WPT system. So that is also a finding that we may want to maybe publish in near future and contribute. We believe that it may add a good value to scientific community. The other aspect was dissipation factor also, basically the loss tangent, and it didn't show much impact. You can see the bandwidth is same, just even like it really is irrelevant. And then the other factor was thermal conductivity. Essentially, it has no impact in general. Of course, within the operating, of course, like range of temperatures. But for a reasonable temperature range, this didn't play a role. So you can choose your material accordingly, like by keeping these aspects. Then finally, if you see this, where are we heading? So first thing is how to design. I showed you through one example, and this slide gives a step-by-step design process. How do we do that? This is a flow chart. This can be found in recently published, I think May or June 2020. It is available in Explore, IEEE Explore, and you can find that these are a very robust design process. Using this, you can easily and relatively quickly design DGS-based WPT systems without worrying about intricate details of DGS techniques. And essentially, to wrap this up, where are we heading? Like future, where is it lying? So if we see this, research directions usually, one thing is performance enhancement. Of course, we want to enhance the performance. And performance, they are, as I mentioned throughout this talk, there are three directions: efficiency, the power transmission range, the distance we call it, and the small circuit size. So these are actual, and these will remain challenge forever, and people will keep coming with different techniques, and of course, the thirst of this cannot be quenched. We will always have, and that will be very much welcomed by everybody in scientific community. Robustness, basically you want your WPT system to be reliable. It's not that, okay, right now I use it, I get 80% efficiency. I just change some, work operating condition, and suddenly it became 50%. We don't want that. So, and usually robustness in that sense, misalignment concepts, they are very important. Actually, it's very challenging still. Many research are ongoing. And then we need to find the mitigation approach to, this misalignment thing as well. Safety is extremely important. You cannot have high power, thing charging to your biomedical thing. It has to be always low power thing. And in the receiver side, say for example, you have to overcome the back lobes usually associated with those receiver antennas. They may damage the biological tissues. Say for example, if you are a pacemaker, it is subcutaneous cells will die. So that should not happen. And then useful frequency. We designed something for X and Y and Z frequencies. It makes no sense. It has to be practically useful. If you have top quality performance but not useful frequency, it makes no sense. It has to conform to some applications standards. And then, of course, there are experimental evaluations. And then, of course, there are always analysis and techniques. I just touched upon very small segment of DGS shapes and its base design. But then you have multi-band WPTs under various scenarios. So these things have to be looked in detail. And finally, just to conclude what I went through in this talk. Actually, I just tried to touch upon some of the fundamentals related to wireless power transfer in general and near field wireless power transfer in particular. Then I moved on to the challenges associated with this approach and the design of such systems. Then how the recent solutions are addressing them. And then I focused primarily on DGS-based WPTs, where this domain is heading, what is the approach, what is the future. Then some of the observations and insights from our laboratory work, I also presented on that, just for the use and information of the audience. And then research directions. This is actually something that has to be handled in detail, and this field is wide open, and it will be it is very fascinating domain, I will say. The advent of 5G and associated technologies and the application scenarios opening up due to IoTs and biomedical. This is actually a very fascinating field in RF and microwave domain. So with this, I end my talk, and I thank you all for listening, and I will be available for some of the questions if time permits. Otherwise, my email is there. One can always get in touch with me. Thank you very much.
Thank you, Professor Hashmi, for delivering a wonderful talk on WPT. Several aspects on WPT techniques you have covered in your talk. In continuation to that, I would be happy to share some of the feedback or some of the queries from the participant sides based on your talk. The first one is DGS can have SRR or CSRR? Hello?
Yes, hello. Am I audible?
Yeah, you are audible.
See, split rings and those things, they can always be useful, but in the context of WPT, they will, you see, we have to be very, very careful about not making system complex. That will create additional complexity. So otherwise, it's actually, it will, I see that they can improve the performance significantly, but they will bring a lot of challenges. That's why I think researchers have not touched upon this. Initially, I think in initial report in 2012 and something, when DGS-based WPT people were exploring, these things came in discussion in some of the talks I hear in some European antenna propagation. There was talk and tutorial on this. And that's why people did not touch upon. But I think it's very interesting thing to revisit again. But in general, I think, if I remember, it will create a bit more complexity.
Okay. Second query is, in equivalent circuit modeling through EDS, substrate is modeled as ideal transmission line or microstrip transmission line?
Now, eventually we have to go for, microstrip, ML. See, ideal will not help. It doesn't take into account various aspects. So it has to be a real thing, not ideal.
Okay. While designing an antenna, we consider it as a single port device and optimize S11 for matching purpose. How do we analyze the S21 for this antenna as shown in slide number 24? Because antenna is a one port device.
Let me see. Let me just see which one is that. So, so actually, it's very interesting. So that's why I said that, you see, you are using this as a resonator. The use of concept, but then you are using it as a resonator, not as antenna per se.
Okay. The next query, Are there any other options available for rectification in energy harvesting applications other than Schottky diode?
Yes, actually, it has been identified that due to nonlinear behavior of diode and the impedance, especially the input impedance of the diodes, they are actually not very useful for RF energy harvesting purposes. So there is second direction of research that is happening that is based on power amplifier based rectification circuits. And power amplifier in class F mode of operation, they work very well for rectification. The only thing is, normally for amplification purpose, we always look for, if we draw this 4-quadrant Cartesian system, then we always look for voltage and current in quadrant 1. But here, like for rectifier purposes, if we are operating class F and inverse class F, then we will see this voltage in quadrant 1 and current in quadrant 3. And that's how we have to optimize the circuit. And they have potential to overcome this low voltage and low power scenario. So this power amplifier based rectifiers will be actually very, they seem very promising.
Okay.
And there are a number of papers available in IEEE Explore. Some of them very, coming from, I think the first paper on that came from Manu Tenteris from Georgia Tech.
Okay.
And that's a very good paper on class F based rectifiers.
Okay. Sir, last query. That how is there any way for simulating transmission loss in CST?
Frankly speaking, I'm not aware.
Okay, no problem at all. Now, with this, I would like to conclude this second lecture of this session with saying a very thank you to Professor Hashmi for nicely clarifying the doubts of the participant too, and prior to that for wonderful delivery of the lectures. Now, before saying bye-bye to you, I would like to invite you for attending the valedictory session this evening at 9:45 p.m. as per our Indian Standard Time using Google Meet link, which I have already mailed to you. Would you be comfortable for that, Professor?
Yes, thank you very much. I will try my best. And it was an honor for me to present this to the audience. I hope that we will remain in touch, and I will try my best to attend the valedictory.
Okay, bye.
Thank you, bye-bye.
Okay. Professor Siddiqui, are you there online? Hello, Professor Siddiqui. Am I audible? Oh, okay. I think there is some network issues at Professor Siddiqui's side. Let me make a call to him. So I now take the privilege to welcome our next and last speaker of this workshop, 1 week long workshop, Dr. J.Y. Siddiqui, Associate Professor at Institute of Radio Physics and Electronics, Calcutta, India. Presently, he is an visiting professor at Royal Military College of Canada since last couple of months. J.Y. Siddiqui is an Associate Professor in the Institute of Radio Physics and Electronics, Radio Physics and Electronics, University of Calcutta, India. He received his Master of Technology and Doctor of Philosophy degrees in Radio Physics and Electronics from University of Calcutta in 2000 and 2005 respectively. He joined the Institute of Radio Physics and Electronics as a lecturer in 2004. He worked as a postdoctoral fellow and then as a visiting scientist at the Royal Military College of Canada at different periods during 2008 to 2014. He has more than 100 publications in peer-reviewed journals and conferences. His research areas include ultra-wideband antennas, ultra-wideband radar, frequency reconfigurable antennas, and multifunctional antennas. He is a co-principal investigator of stratosphere troposphere radar project at the University of Calcutta. He is a senior member of the IEEE and currently serves as chair of the APS and MTTS joint chapter in Calcutta in IEEE Calcutta section. He is currently also the chair site chapter IEEE Calcutta section. Is the Region 10 coordinator of the IEEE APS chapter activities committee. With this, I welcome you, Professor, and invite you for your talk.
Thank you, Dr. Taimur. It's a pleasure. Can you hear me?
Yeah.
Hello, am I audible?
Yeah, you are audible.
Okay. Thank you so. Yes. Thank you so much, Professor Taimur, for arranging this workshop and inviting me to this event. It has been a long, long due, and your effort has culminated in this workshop, I'm sure, which is beneficial to the audience who are there listening to this presentation for the last 4 days. And I again thank you for giving me a scope slot to talk on some of the research that's going on in these areas. My active research is on antennas, and that's what I'm going to talk on. And it could have and it should have application in energy harvesting applications, RF energy harvesting application. That's the focus theme of this workshop. Is my presentation visible?
No. Your presentation is not visible. On bottom side, right corner.
Yes.
Yeah, I think so.
Right. Is it now visible?
Now it is coming.
Okay. So once again, thank you so much, Dr. Taimur Khan. And my topic is on some advanced antennas for RF energy harvesting applications. I'm sure the audience have listened to my preceding speakers of this event, Dr. Nasimuddin and Dr. Hashmi, who has dwelt on this topic and gave their excellent talks and the scope of work and things and the research that they're conducting in these areas. So my presentation will be similar to what the audience have been hearing for last 4 days. But still, there might be something new to come out of this presentation, and maybe some nitpicking can be done from the audience. And I'd be glad if, they have some questions and some queries, and they benefit from this presentation. So proceeding on this presentation, again, I'm reiterating the facts and the statements that has been made by the preceding speakers, like the introduction, basically why do we use energy harvesting. So it's an approach to collecting energy in situ for remote or wireless applications. That's we talk about smart cities and IoTs and whatnot, basically converting any city to a smart city, which especially in digital scheme of things like Digital India, that has been the approach of present government, not only in India, everywhere in the world. So it's all energy. You've seen that the advancement of capturing or collecting energy from different sources has been picking up for last few years. In fact, we know how much this solar energy, solar panels, and the research on that work is progressing, because there is an abundance of energy in our environment. There's abundance of energy from the solar, from the sunlight. So why not tap it? Because there is a dearth of energy, and energy is something which drives the world, at least the technological world. The progress, the advancement in all our life are related to the amount of energy. We still have villages which has no electricity. So what we are as technologists are looking for is to capture or resource energies wherever available and make it useful for mankind. So this energy harvesting, especially in the scheme of things for the radio frequencies, basically collecting energy in situ. Like it could be in situ, it could be any place at any location, at any random location. You could have the opportunity to collect energy from the nearby environment or the ambience. So this energy can be harvested, can be extracted from environment. Like I said, the solar, the piezoelectric, the vibration, the thermoelectric, electromagnetic, that's RF, which we'll focus on in this presentation, and also the wind energy. We know, like not only the solar, but even the wind panel, the windmills that come up and they generate huge amount of electricity, and that could help, especially in the coastal region. You have this windmills erected, which would supply, power to, close to that region, and which are basically, given to the grid also for consumption of power. When we talk about RF energy and energy harvesting, we are looking at very low power. So this low power consumption is basically all for our wireless sensor networks, which would be our handheld devices, phones, small gadgets. We are not looking at very high power consumption, because high power consuming electronics would not be suffice, with the available energy that's found in the environment or in the ambience in terms of RF energy. So this external power supply, which is the supply demand increases with increasing sensor networks. Not only handheld devices, now we are talking about drones. This drones will, again, we have this drones used for many purposes. They're using for unmanned, these are known as unmanned vehicles, and they're used for agriculture, and they're used for other surveillance projects. However, if you could have some source of energy from the ambience which can, power these drones, similar to how the solar power is energy, the solar panels for satellites, which are in space, it could, serve the purpose of remove the batteries, make the drones lighter, and make it work more efficiently. So ambient RF energy could be provided by commercial RF broadcasting, TV stations, GSM, and Wi-Fi. Then where will this energy come from? So this ambient, the RF energy that is in the ambience, could be provided by RF broadcasting television stations, which basically transmit UHF. The GSM bands that's you use for your mobile cell phones, for the GSM1 and the GSM2 bands in the 900 megahertz and 1800 megahertz frequencies, which are basically transmitted by the base stations. The Wi-Fi, which is basically the ISM band of 2.445 gigahertz. These are the source of energies. Wi-Fi you have at home, you have a router at home. How useful will it be if you have a batteryless phone which could be charged by the radiating energy that is being transmitted by the Wi-Fi router that's situated in your home? So these are the applications and the thoughts that engineers and technologists have thought of, and the research basically, this feeded the research in this domain of RF energy harvesting. Moreover, these wireless sensor networks, they may be inaccessible in places with harsh environments. I'm sure, like you've heard about the square kilometer array. This, like you've heard about, the satellite communication, which is basically providing internet to the, to the part of the world which is not still eliminated this RF energy. So RF energy basically everywhere. You have this Tesla, the SpaceX agencies. These are, like they have already launched this low Earth orbit satellites, like to provide internet to the world, and like even to regions where it's still not illuminated by RF energy. So basically this RF energy is everywhere in the world. So if you have an inaccessible place with very harsh environment where it's impossible to lay cables or impossible to provide a link, microwave link or any other RF links, you can have this existing ambience RF energy which could be harvested to power low power device, consumer electronics or devices in those regions. Again, there's another terminology that's used for this energy harvesting, scavenging. Or scavenging is basically extracting or finding something useful from the waste. And harvesting, this harvesting is basically at a minimal cost and maintenance, because you really don't have to maintain anything, because until and unless you have a dedicated transmitter, if the RF is coming from an unidentified source, you really literally don't have to maintain the source because it's not in your control. So there's the typical block diagram of an energy harvesting system will look like this. You have an incident or an ambient electromagnetic energy, for which to capture that energy, the first front end you need is basically a receiving antenna. A receiving antenna which captures the energy. It has to be converted, it says it's RF. It has to be converted to DC power, for which you need a rectifying circuit. For the active devices that's on the rectifying circuit, and to match it for efficient transfer of power from the antenna to the rectifying circuit, you need the matching circuit. That is, if the rectifying circuit, the active device in the rectifying circuit, that impedance of the active devices, you literally have to match with the impedance of the antenna. So you have to design that matching circuit. And then that rectifying circuit will convert the RF power to DC power, and you'll send it to the load, which will be the power management or your device or your consumer electronics, which needs that power. So when you have this, so many things in place, like you have the antenna, you have the matching circuit, you have the rectifier, what happens is every component has its own limitation. Every component has its own efficiency. And these efficiencies, when they're cascaded, they can create a, a issue in terms of the efficiency for the end user product. So when you have an antenna, the antenna always comes with an efficiency. That is, an efficient antenna. The design of the antenna will tell you how the radiation efficiency is. And depending on that radiation efficiency, it will be able to capture that much amount of ambient power. So your efficiency of the antenna should be high. So when there's incident power impinging on the antenna, electromagnetic wave impinging on the antenna, depending on the efficiency of the antenna, will capture that power and pass it to the matching circuit. It's imperative that your matching circuit should be lossless, because you want to minimize the loss in the matching circuit, because the capture RF power from the antenna, when it passed on to the RF DC rectifier, you want the absolute, the most amount of power, you want to maximize the amount of power to be passed on to this rectifier, because your whole objective is to capture maximum amount of power and convert it to DC for your consumer electronics or for your load or power management. Now, when it goes to the rectifier, there's another efficiency issue, because again, this rectifier circuit has its own devices, active devices, and they have their own efficiency factor, which will again, probably create a loss in the captured power. So you have to maximize that efficiency too. Again, it has to pass through a low pass filter because you want DC, so you basically we convert it to when you want DC power, you don't want any high frequency or harmonics to pass through, so you block it, and then the DC power goes to your load. So the end efficiency, this E for RF to DC, is given by this factor V squared by RF and multiplied by PRF. So this V squared by RF is basically the output DC power, and the PRF is basically the input RF power. So the factors which affect the efficiency, or which the total efficiency are the antenna efficiency, the impedance matching, and the power efficiency of the rectifier. So now you have the input power, RF power, your output DC power. So if you calculate them, you would now understand the total efficiency of the whole system once you have the efficiency of these individual factors. And the better you can maximize the efficiency at each individual stage, the better your output efficiency will become. So these are typical, understanding of how the system works. Now, what kind of source? There are basically, it has been divided. What kind of source would you need to capture this and this RF energy which you want to harvest? There are two kinds of dedicated, two kind of sources. One is dedicated, one could be undedicated, or identified and unidentified. You have the ambient RF source, which is unidentified and not dedicated. They're freely available, if you walk near outside a cafeteria, Starbucks, or a McDonald's, what you get is that you can, without even going inside from outside, you can still get onto the network. You can, get the free Wi-Fi. So that's energy which is basically, coming out, which is not defined within the enclosure, but which is proliferating outside the enclosure, so you can capture them. So that is the RF energy, RF source. You have the base station. So if you can design a system which is working at 9 or a GSM 1 or GSM 2, basically you can get this RF source from anywhere. You can, stand as a road and you can capture this energy. So it's freely available. You get it from the TV, the Wi-Fi, unpredictable sources, but these are all for very low power, because I'm sure those who are working in the field of RF and microwave, they know that there's a term called EIRP, that effective isotopic radiated power. There's a certain amount of limitation of electromagnetic energy that you can impinge from a transmitting source. So these are low power because it's not intended for your device, but it's intended for somewhere else. It's intended for the GSM and GSM2 usage, but you are scavenging that power. You are basically, proliferating some of the power from the source, which is basically intended for some other destination. And then technologies are now thinking of having this dedicated RF sources. And what if you have a transmitting tower which are intended for your wireless sensor networks? This transmitting antenna could be it could be power on demand supply. Like it means scavenging dedicated. You're not really stealing the power, which is intended for some other devices, but you are now basically, you can stand outside and you can get that power, to charge your device from a source which is dedicated to charge your device. This will mostly be in the ISM band transmission, and the source will be predictable because just like the way you have a base station for your cellular operation, you could have a base station for charging your phone, which will be, again, it dwells on the definition of the near field and the particle power. Like you have this near field charging devices. You have for Samsung and iPhone, you have the charging mats, the inductive coupling. Like you place your phone on the charging mat and it could get charges. It could get charged. So likewise, if you have a dedicated source which could transmit high amount of power, you could have multiple wireless sensor networks which could be charged, like from the dedicated source. And of course, the advantage of this kind of dedicated source will be the high power density that you could derive from such kind of stations, which are dedicated and could be on demand. Again, whenever there's a talk about transmitting power, there are health issues, hazards, which are looked upon, and there are dedicated numbers, which are thresholds, should be maintained, known as the emission masks. So the FCC, the region of North America, has an emission mask which defines the maximum allowable radiated power for ultra-urban devices, which is the power spectral density, and has to be compliant with the emission mask. So that's useful for the effective isotropic radiated power, which is nothing but the product of the gain of the antenna and the transmitting power. So for every frequency, you can see that for every frequency band, there's an indoor mask and outdoor mask, which translate to power in watt per megahertz. That's shown in the right-hand extreme right column of the table. So this emission marks pertains to frequency. So whenever any antenna designer designs an antenna with a certain gain, your intended use of that antenna in location, in frequency, will define how much power you can emit from the radiator. So either you change the gain of the antenna, or you make sure that your transmitting power would be tuned to that level that it doesn't cross these thresholds. And these thresholds are separate for indoor application and for outdoor application. Now, there are basically three kinds of schemes that's that's in vogue right now for this microwave energy harvesting. You have the wireless power transfer scheme, which you have, like I said, a dedicated source, maybe an access point or an undedicated source, and it will only transmit energy to the users, the wireless network sensor network users. So it would from the ambient energy you can harvest, and it's only the energy that will be captured by the devices. That is, WPT will transmit energy only. The second scheme will be the WPCN scheme, which is basically wireless powered communication network, which basically transmits energy as well as receive information. It could be useful for a dedicated source, like it could be a two-way communication, like it can capture energy, but it can also provide information to the access points. Information and power transfer. So can be again, like you're transmitting information or energy and getting information or energy from the wireless network users. Now this WPCN could be managed in time. There could be like in time management, like at T1, time T1, they can send energy, and time T2 they can collect the information. Likewise for Swift, again, it may not be time management, but still on dedicated or on demand, they can either transfer energy or from the access point and from the to the wireless sensor network users. Now I come to the topic of my on antennas that I use, basically the scheme and the antennas and the type of antennas that you could use for energy harvesting. Let's talk about home automation. Again, this probably these schemes have already been told by Dr. Nasruddin earlier in the day, but like what kind of antennas, like every antenna has its own mode of operation, has its own radiation pattern, has its own frequency. You design an antenna for a certain frequency, and then the placement of that, depending on the radiation pattern, you have to place the antenna in a proper strategic location, which could be basically, sorry, which could be efficiently working as a radiator, because even if you design an antenna which is highly efficient and radiating at a certain, so like radiating either in the elevation plane or azimuthal plane, your sensor networks, your objective is to empower the sensor networks which are available in the region. So you should maximize the beam, the radiated power, which should reach the sensor network, impinge the sensor network, so that they get the threshold power to either switch on or switch off or whatever to charge a battery. So there is a paper in IEEE magazine which talks about conversion of a signal from a multi-directional receiving signal. There is an issue like in home automation, like homes equipped with automatic controls, like say for shutter, for lights, etc. And if these devices are remotely controlled, the sensors are always on, and they are waiting for an order from the remote control, which results in stand. Now, when signal will come, basically these devices are always on. There is a scheme to minimize the loss of the standby and off modes by using a sensor network through an emitter, which will be charged, which will impinge RF signals to the sensor networks on demand, depending on when they want to switch on and when they want to switch off. So the receiver at the ceiling, it will basically emit energy, but then this receiver has to come from the emitter, which will be defining when you want to use the remote control and when you don't want to use the remote controls to switch on or switch off the wireless network, sensor networks. So these are all, though we have an abundance of RF energy in free space, in ambience, but still the management of this RF energy becomes very critical, because there will be wastage of power if the device is not supposed to work basically in the near future, because even if it's in standby mode, there will be some amount of leakage power which will be consumed by the device, and you don't want that, because as we know, as technology progresses forward, with more wireless sensor networks coming in play, this could be really a good challenging issue. So in this paper where they used, if I focus on the antenna system, they designed this multi-directional, like Yagi type antennas, printed Yagi type antennas operating at 2.45 gigahertz, and placed it on the ceiling of the room. And you have this direct and reflector, which are basically radiating in such a way that you can see from that radiation plot, it's basically have an azimuthal direction of the radiation pattern in sectors, so it's basically illuminating the whole room. Like if you have worked on with microstrip antennas, you would know that the mode of operation, the fundamental mode of operation, will have a typical radiation pattern which is in the broadside direction. But if you go to the first higher order mode, the radiation pattern, it will give you a radiation pattern which will have a null in the broadside. Likewise, every antenna has its own frequency of operation, and each frequency of operation will come up with a different kind of radiation pattern. Okay. So likewise, they use this kind of printed Yagi antenna to get the sectoral pattern at each frequencies to cover the whole room. So your understanding of the radiation pattern of the antenna becomes critical, and the placement of that antenna becomes critical, like where you are placing the antenna. If it's placed at the ceiling of the room, you want the illumination of the whole room, so you could have multiple antennas which will be covering the whole of that area of the room, of the volume of the room. And your intended device should have a beam pointing towards the maximum, beam of the antenna so that it can reach the threshold of the power that it needs to either switch on, switch off, or charge. Now, again, this RF, I'll talk about something about the radio frequency identification tag antennas. If it's helpful for researchers who are working in this domain. The radio frequency tag antennas are very useful. That's probably one of the most easily available commercial use of energy harvesting or wireless power transfer. Like they are used for wireless communication to identify physical objects without direct intervention. They consist of reader or interrogator transponders or tags. They operate at certain frequencies. They can be active, passive, or battery operated. So depending on what type of tag you use, that will decide, what would the distance of that wireless power transfer, like what would the working range of in terms of distance of this tags that could be used for our application or operation. So these tag antennas, basically, they are electrically small. So most long-range RFID system has to work on 860 to 960 megahertz region. Again, you have certain frequency limitations. This 100 megahertz again is basically for this RFID system application, but each country allocated a very certain bandwidth of these frequencies, where they have to design the stack for their own useful operation. Like the FCC allows 902 to 928 megahertz. In the US, which is basically 26 megahertz of bandwidth, the European community, they allow only 3 megahertz of bandwidth, 861 to 868. In Japan, it's allowed only 2 megahertz of bandwidth. So now the issue comes, this RFID tags have should be cheap and should be small. So there comes the whole concept of electrically small antennas. That they design these antennas very, which should be small, but still should be efficient to at least interrogate or talk to the transponder. So at 900 megahertz, if you are talking about this frequency which has been allocated, you can see the wavelength is basically 33 centimeter, which would define your antenna dimension if you consider half wave dipole, 15 to 16 centimeter long. That is too large. So they should scheme and to design an antenna which could fit small, which can be made small, but still work at these frequencies. So these are the challenges that antenna engineers face with the design systems for these frequencies. Again, this tag antennas should be variable and uncontrollable dielectric environments. Like this tag you have seen, it's basically placed on clothes, it's placed on metal, it's placed on liquids, bottles, PET bottles. So now if you know about the reactive energy and the radiative energy, we know about the Fresnel zone and the Fraunhofer zone, the near field and the far field. So the whole concept of antenna theory changes when you design an antenna and place it. Say you design an antenna for an ideal condition, you test it on a test bench in ideal condition in an anechoic chamber, and you place it on a bottle or on a metal. The reactive energy in the rear field changes, which changes the impedance of the antenna. So your whole antenna would be, may shift and would shift the frequencies. So how do you define the tolerance of that antenna? So these are the challenges that are taken up by the researchers, like to define, and that's why they are very actively using research now. Now, variable orientation. Again, even if you maintain the impedance of the antenna, what about the orientation? Like each antenna will have a certain kind of polarization, linear, elliptical, or circular. And in circular, it can be right-handed. The orientation of the antenna for a channel, you don't place, and the orientation of the maximize the extracted power, which will, or the power that should impinge the tag and tag orientation. They increase the complexity of the IC and the cost of the antenna structure. Again, these are the kind of type of tags. And like I said, the communication protocol has their own defined frequencies. You can see for India, the frequency that's allowed for RFID is between this frequency of 2 mega, having a 2 megahertz bandwidth. The challenges which is tag antennas are the cost. They have to be very low cost. We cannot design an antenna on an RTGOID substrates and make it cost effective and place it on a product which costs $1. You know, the antenna cannot exceed literally the cost of $5 if you have it on a $1 product. And that has been the bane of antenna researchers, because the product and the cost of antenna is probably on any device, even on your cell phone. It's probably has the lowest cost of all the devices that's integrated on a cell phone, even the base one. So as antenna engineers, that becomes challenging because you have to design a highly efficient antenna on a low cost material and with a low cost design. So the cost, size, polarization, the matching to the IC load. Again, even if you design an antenna which is a very highly efficient antenna, you need to have the feed line which will transfer power from the antenna to the IC device. If you have an IC integrated tag for impedance matching, this is required for efficient transfer of information and power. And getting along with neighbors means the mutual coupling. You can have two tags on two products which may be sitting on each other. You have to take that into consideration too when you design a tag antenna. So if you go through this chapter of this book, there's the tag requirement, the IC requirement, the passive tag integrated circuit typically requires some amount of power. It should be 10 to 100 microwatts of power, DC power for normal operation. And since it's a passive, it has no battery. This supply is derived by rectifying the received RF signal using multi-stage diode charge pump, which is basically a rectifier. And this efficiency is basically 20 to 30%. So literally, if you want to have a tag IC 200 microwatt of power, you need to collect 30 to 300 microwatt of RF power to use in the efficiency range of 20 to 30% to excite to get the amount of DC power for normal operation. So the maximum power that can be collected by resonant dipole is the product of the incident power density and the effective cross-sectional area of the antenna. And this PRX is it will be the U that is incident power density, and A subscript is the effective cross-sectional area of the antenna. So the incident power density is proportional to the square of the incident field. That is, if you have a electric field curve, if you know the incident fields, divide by twice the free space impedance, that will give you the incident power density in that in a particular region. And this incident power density at a distance d from a transmitting antenna with the power PTX and gain GTX is given by this equation. The inverse d square law, and the effective cross-section for the matched resonant antenna for a particular frequency is given by this equation. So it's basically 150 centimeters squared, depending on lambda. If it's lambda, it's 150 centimeters squared at 915 megahertz. So you have the incident power density. Now you have the effective basically gain of the antenna. So you can get the amount of receive power that you would receive with an antenna that you design, and depending on the power density. So with this calculation, you would know whether this sufficient amount of power, or like to activate your device. These are the some of the RFID tag antenna that's used. You can see, like this is the left-hand picture. It's a wrapped lettuce. So how much does a lettuce cost? It's probably $1.5 or $2. And you have an embedded RFID tag antenna, which is embedded inside that inside the level. So you basically like when you go home, you eat the lettuce and throw away the tag. So that's why they have to be cost effective. But still, just think of the engineering that an antenna engineer has to do to embed this kind of a tag inside just a wrapper, and the amount of like brainstorming you have to do to design an antenna, and it's going to be thrown away. So this electrical small antenna, usually less than 1/3 of a wavelength, should again, like I said, operate in very uncontrolled RET environments. So these are the challenges for antenna engineers that's coming up. So how do you do this miniaturization or shorten the length of a half-wave dipole? One of the way to do it is using meandering dipole. That is, if you have a 16 centimeter, you can see your length of a dipole, you can basically meander it to make it small. So at each meander, you have to consider the arms of the meandering so that you do not, because we are talking about electromagnetics. And electromagnetics, basically, we are dealing with vectors. So 1 + 1 could be 0, or it could be 2. So it depends on the constructive and the destructive interference. When you talk about constructive and destructive interference and the currents on the dipole, on the arms of the dipole, the cross currents, you design your dipole, meandering dipole in such a way that you have a cancellation mechanism so that they don't interfere with the radiating, like with the radiation from, from the co-polarization or cross-polarization radiation of the dipole. Again, some more examples of the underlying dipole that's been used with capacitive loading and inductive loading, spiral inductor. They all lead to capacitances and reactances, increase the bandwidth, increase the, lower the frequency. That's how you do it. It's, like 1/LC. So how you design your resonant circuit or resonant antenna will define your inductance loading and the capacitance loading on these antennas. Again, some new antennas that I'm scavenging through the literature. Here's a quad-band antenna RF energy harvester, which was designed using genetic algorithm. So again, you have a feeding network and you have a quad-band RF energy harvester designed with the use of genetic algorithm, which works in the 900, 1750, 2150, and 250 megahertz bands. So these are optimization tools. Now, antenna engineers have been using your theory. There are these optimizing tools which can design your antenna depending on your requirement, or depending, and then it could be like working on antenna synthesis. So, like new theory coming in for designing of your antennas so that they can be efficiently working at multiple frequency bands. Once you design the antenna, one challenge that comes is the feed network, because if you have a known geometry of an antenna, you know how the feeding mechanism works, the type of feeding that can be used, the type of excitation that will provide the different kind of feeding. But then with this kind of, optimized antenna, which is basically machine optimized, algorithm optimized, you have to understand the feeding network and how to feed that antenna so that it will work in the proper orientation and will give you the desired result that you are designing this antenna for. And again, there's another paper where a group in IIT Bombay who designed a differentially fed antenna for energy harvesting. So they use a directive antenna, which is used for increasing rectifier efficiency at the expense of coverage. This concept of differential feeding, sampling, and differential rectification is used because most IC chips will have differential inputs. So if you can design a differential antenna, it makes sense for the matching network to be easier and to provide a better, efficiency in the system. So the antenna was designed for GSM 900 bands, and the peak gain over the whole frequency band achieved it was achieved for center frequency with a gain of 8.5 dBi. So differential input to the rectifier is preferred for enhancing the efficiency of the energy harvesting circuits. Then Dr. Nasimuddin talked about this antenna, so I'll skip this antenna, use this RCP circularly polarized antenna. Again, this polarization sensitive antennas, and depending on the application and how you want to use the antenna, the orientation of the antenna, the location of the antenna will define, the design, the geometry, and these, physical aspects of the antenna. There's another antenna for smart building application, which came out in AP Magazine 2018. They use the multiple input and single output approach for full wave rectification. They designed two antennas, which is integrated into one for cellular and Wi-Fi harvesting. So the antennas used for cellular application were taper slot antennas, linearly taper slot antennas. As you can see, there are slots, tapered slots, and having 4 taper slots oriented in 4 different sectors, separated by 90 degrees. So for full azimuthal coverage, this can be used for harvesting energy from the cellular transmission. And you have microstrip antennas, which would be a broadside radiator, because taper slot antennas are end-fire radiators, and you have integrated microstrip antennas, which are broadside radiators, and they could, they are for capturing energy from Wi-Fi routers. So it's an integrated antenna system where you have the for LTSA for capturing azimuthal power from GSM bands, and 8 microstrip patch antennas with broadside radiation, which capture power from Wi-Fi, 2.45 gigahertz or 2.5 gigahertz. Now, this is some of our work that I'm going to present. We have a book, Professor Chinmay Saha and Professor Antar. We wrote a book on multifunctional antennas recently. We designed sub antennas, and which we feel could be useful even for energy harvesting purposes. You can check this paper. This came out in the transaction in antennas and propagation in August 2014. It's compact SRL loaded ultra-wideband circular monopole antenna with frequency notch characteristics. The novelty or the newness of our design is we showed that without tampering the antenna structure, the radiator or the ground plane, you can basically get a frequency notch on an ultra-wideband antenna. Because when you design an ultra-wideband antenna, there might be some impingement frequency which you want to filter. So we propose a technique where you use split ring resonator on the feeding section of the antenna, so that it can filter out the frequency that is undesired in the radiation. You don't want a certain frequency in the whole range of ultra-wideband frequency that you don't want it to radiate. So you design a radiator, you design a resonant inclusion, which in this case is a split ring resonator, which will filter out the frequency. The beauty of this design is you don't have to tamper with the radiator at all. So you change the geometrical shape of the split ring resonator, it will filter out the desired frequency that you don't want to radiate. And it can configure for multiple notches using multiple pair of SRRs. Like this was the design. You can check that paper for the equations and for design guidelines and parameters. So we have a CPW line and a printed monopole antenna. So on the back side of the CPW line, we strategically placed 2 split ring resonators, which help us filter out frequencies. Like you can see the measure and the simulator return loss curve, reflection coefficient characteristic of the antenna without the SCRR and with the SRR. You can see the SRR, which was designed for 6.2 gigahertz, will show up a notch at that frequency. And this is scalable. This notch is scalable. You can basically move notch from within this range from any frequency to any frequency, for high to low frequency. You just have to change the shape of the geometrical shape of the design of the split ring resonator. You don't have to do anything with the antenna or the radiator. But at the same time, we maintain the proper radiation pattern of the monopole. Like at different frequencies, you can see that it doesn't even tamper the radiation pattern of the monopole antenna. It gives the same, directive in the elevation plane and non-directive in the azimuthal plane.
Professor Siddiqui, sorry for interrupting you. Your voice is not clear. Can you please adjust your microphone? Because maximum participants are making the same complaint that voice is not clear, not audible.
Is it okay now? Can you ask them?
Might be. Okay. Yes, yeah, quite okay now.
Hello, is it audible now?
Yeah, it is now fine. Okay, carry on. Okay, sir.
Okay, thank you. How much time do I have? Hello. Yeah. So
Five,
this
10
is
minutes.
the gain was
Maximum
okay,
5 minutes, 10 minutes.
Okay. Thank you. This is gain versus frequency. As you can see, that the gain of the antenna, there's a dip in the gain at the resonant frequency of the SRR. And this will show that this antenna you can scale the frequency, notch frequency at any undesired frequency if you want to filter out. You just have to change the shape of the split ring resonator, which will give you a notch at that frequency. Now, this is a very interesting antenna, which again, taking cue from this notched antenna. This is a multifunctional antenna which we designed, which will give you a complementary characteristic. Like, we literally transformed an ultra-wideband antenna into a narrowband antenna, but still maintaining the radiation properties of that antenna. So this came out in Antennas and Wireless Propagation Letters in 2015, a novel ultra-wideband printed antenna with a dual complementary characteristic. Like, you can switch this antenna like using an active device, but we have shown the proof of concept, prototyping an antenna which can basically toggle between working as ultra-wideband antenna, notched antenna, and a narrowband antenna using one single antenna. So that is why this is a very, very interesting antenna technique, which could be used for this energy harvesting application. Again, you have a split ring resonator on the transmission on the feeding line. That is, here we use a coplanar waveguide, and when we short basically the feed network, the coplanar waveguide, basically there should be no transmission. But when you place a split ring resonator underneath, it radiates only at that frequency while filtering all the rest of the frequency, that could transmit to the antenna or propagate to the antenna for radiation. This could be used for CR application. Here you can see one configuration is with the radiation, without the shorting post, you have a notched antenna, ultra-wideband notched antenna, but with a shorting post, you just have a narrowband antenna. And this narrowband operation of that antenna, again, could be tuned by designing, just tweaking the dimension of the split ring resonator. So you have a shorting post on a coplanar waveguide. Beneath it, you have a split ring resonator. You just change the dimension of the split ring resonator. Your narrowband frequency will move, like for the range of the ultra-wideband operation that it has. So now one antenna, that's why we call it a multifunctional antenna, because with this antenna, You can radiate ultra wideband range of frequencies as well as only a narrowband range of frequency depending on your application and how you want to use it. So we call it a dual complementary antenna. And then we used pin diodes with a bias T to bias the antenna to show in real time how the like this antenna works. Like we call it a reconfigurable antenna, but again, you can't you don't have to tamper with the radiator or the ground plane. Just you have to place this diodes instead of this the shorty post, and you have the split ring resonator underneath. So what you get now is basically dual complementary antenna. If you switch off the diode, you'll get a notched antenna, ultra wideband range frequencies of operation with a notch. You switch on the diode, you just get a narrowband frequency of operation. So that's the interesting part about this antenna. And there, we have used a circular radiator, but here you can replace with any radiator. This is a generic antenna. You can replace any radiator. If you have this type of a feeding mechanism, you can get ultra wideband or whatever band of frequency you want. You can get a notch frequency. And at the same time, you can also switch that antenna to use for a narrowband operation. I'll play a small video where you can see the operation. This is the switch off mode. I switch off the power, switch on the power of the bias T. You can see the response, how the response is changing. So that's a gain that is ST1 of the antenna. So that's why I say that this kind of an antenna is very interesting, because you can literally, we call it multifunctional. You can use it for application. Just think of one antenna which could give you a wideband response as well as a narrowband response, just by switching on and switching off, some active device on the antenna. You can use pin diodes, you can use MEMS, RF MEMS, that would be useful. And this type of antenna could be very much useful if you can scale. We've done it for 6.2 gigahertz, but if you can scale it down to 2.45 gigahertz, you can have a very narrow band small radiator which can capture energy for harvesting. And you can see there's a very sharp band, frequency. Again, there's another work we did for ultra wideband taper slot antennas. We designed an antenna which has a design guidelines for operating from 400 megahertz to 10 gigahertz. So this is one of the smallest form of printed antennas, which goes down as low as 400 megahertz and goes up to 10 gigahertz of work. And again, this is a work done by our group, and it came out in 2011 at AWPL, and maintaining a good gain over the whole range of frequency. So again, if you need a very wide, super wideband antenna, this is one of the antenna which could be used for, like energy harvesting application with a good radiation pattern. Again, there are some more antennas which were, again, I scavenged from other work that has depending on an array or Koch type patch antenna which were used. And this paper, I'm showing this paper because it's done by a group and led by Professor John Volokis. And they have defined a rectifier architecture using Koch type array antennas, and they defined a term which is known as the antenna topology indicator. So again, Dr. Nasimuddin and Dr. Hashmi has already dwelt on this topic of RF combining circuit and DC combining circuit. Now, which one to be used and which one will be more applicable? So there is a figure of merit that can be calculated depending on the efficiency of your system, of the antenna, whether you want to use the like a diode rectifier before the RF combining or after the RF combining. either you want to combine the DC or you want to combine the RF and then do the rectification. Depending on the application, your best choice will be depending on the radio propagation model, the efficiency you derive from there, the efficiency of the harvesting RF, and the efficiency of the diode, rectification RF. And if you they coined a term known as rectangular topology indicator. And this is a function which is defined as the ratio of the final available DC power from the two topologies, from the RF topology, from the RF combiner topology and the diode combiner topology. And for different, azimuth and elevation angle, when you can define this RTI factor, then that will give you an indication of which will be the best topology for use at that certain place, at certain condition, because radiant power coming from the, using the Freeze law at that location will give you an, an idea of which will give you more better rectification and better efficiency of the system. So this is very important. Like this is a term which was which are ignored by researchers, because when you design a system, it is not meant for operation at an ideal location or anechoic chamber. It's basically for operation at a certain place where the impingement of RF energy at different frequencies and different orientation in space will define which will be more efficient. Then there's another work on selective rectangular switched beam antenna. Again, you can do, yeah.
Professor Siddiqui, your slides are not full screen. You make your slide full screen.
Okay.
Please.
Yeah. Selective rectangular beam switch antenna. This paper gives you an idea of rectifier selection for RF energy harvesting. Depending on this, as you can, I would, advise the researchers who are researching this area to check this paper, because it came out in APS 2020. And they talk about the best rectifier circuit depending on the input power level, which will give you the best rectification depending on which diode will you use. Should it be a voltage doubler or series single series diodes? And then they have the specified diode, which will give you an idea, and will give you an idea of which one to use and which one not to use for your application depending on the input power level. So these are, again, I did some scavenging from the available literature and providing here in the slides in my presentation to give you an idea. Again, as we go for more power harvesting with different applications and different, one of the things that researchers should keep in mind is the concept of small antenna and the radiant sphere. So we know the Wheeler, Harold Wheeler, in 1947, he basically coined this term of radiant sphere and small antennas, because he said that any radiator whose dimension is small compared to the wavelength is subject to fundamental limits, which is represented by fundamental limit of small antennas. And Chew, Harrington, MacLean, they came up with the equation of the formula which defined the Q of a small antenna, or the Chew limit, depending on the radius of the sphere that encloses a small antenna. So whenever you design an antenna, there will be a boundary sphere which will be encompassing the antenna, irrespective of the geometry of the antenna. Depending on the largest dimension of the antenna, you can define a sphere. The largest dimension will be the diameter of the sphere. So the lowest achievable Q that can be achievable using the dimension of the antenna can be provided by this equation. So this is the Q limit. That's the lead to the quality factor, because small antennas gives a high quality factor, but for antenna you need a low quality factor. That's Q must be low for an antenna, and Q must be high for a resonator, because Q must be low because your antenna is intending to radiate all the energy, not capture the energy. So any amount of holding that energy will lead to high Q, which will lead to loss in radiation efficiency. So Wheeler termed the coin radiant sphere. Now, if you have a small antenna, how would you know that the impinging electromagnetic wave surrounding it will be captured by that antenna? That is, again, he came up with a brilliant term known as a radiant sphere, which is defined as the boundary between the near field and the far field of a small antenna, which is given by the radiant sphere, is given by the frequency of operation. So you have R is equal to lambda by 2 pi. So this boundary, which is enclosed by the subject radiator, is a sphere whose radius is lambda by 2 pi. So that will give you the radiance. So you have to understand the concept of the boundary sphere and the radiant sphere of the antenna. You have to, these conceptual ideas will make you understand how a small antenna or a very small, much smaller than wavelength or the Hertzian dipole would work, how an impinging wave would be captured by that antenna from the nearby environment, depending on the radiance sphere, that is lambda, or the frequency of operation. And this scope of antenna is still, it's a very highly fertile ground for researchers to work on. Now I come to the term of ethical concerns of energy harvesting. This is again another topic. Like there were questions like, well, with this energy that's available in free space, is it which is intended for some other operation? If I capture it in situ, is it theft? Like it can be directly related to main power tapping. We see it, at shanties or lots of places that you tap power from the grid, so that you don't have to pay for it. For energy tapping, we don't, for energy harvesting, whenever you show in an energy harvesting, even as researchers, we really don't pay the company who is basically transmitting the power. Again, this energy harvesting came up with the term of RF scavenging. Scavenging is again waste. So this power, which we are trying to capture, again, it has a gray area in ethics, but still, it's a wastage power. Like if I buy a product from a shop, if I use the product and throw away the product, there could be scavengers who will come and scavenge the product from the garbage bin. But that is not theft, because I've already, considering that power as waste. So this is not theft, and this is ethical, as long as it's not defined unethical by the by the company which is transmitting that power. So it's okay, it's all good until it's defined otherwise. So if we come up like in future with dedicated power source which is intended for energy harvesting, probably things will be more black and white. And this concern, again, the technologies should be familiar with engineering ethics and legal concerns. So prior to advocating, you should consider whether there is a restriction or an objection of that capturing that power. If there's objection, then it's unethical. If there's no objection, then it's ethical. And some of the references of our work, which came out in AP Magazine and AP Magazine, and some of the transaction and wireless propagation letters. I'm indebted to Professor Antar, working at the Royal Military College of Canada, and doing a lot of work and using the anechoic chamber for measurement. My collaborator, Dr. Shah, he has been with me throughout my journey, and we have been working together in this field and trying to see new aspects, new designs, and new objectives. So he's probably one of the most efficient antenna academician in India right now, very active. Dr. Day-5 Silchar is, most active. He's joined the Indian Institute of Science in Bangalore, one of the most promising electromagnetic academician in India. Coming up, he used to be look out for the future. Dr. Devarati Ganguly, she's a very, very active worker, researcher. She's working on MIMO antennas and RF MIMO antenna systems right now. And these are all a very elite and very experienced and very enthusiastic team that we have that I work with, and hopefully will come up some good and new research in this domain later on. And this is the book I was talking about, Multifunctional Ultrawideband Antennas. The audience here can go through this book, have a look at this book. There are lots of aspects of new antennas that has been covered in this book. And if there are any questions, you can mail me at this email ID, jys.rp@gmail.com. And thank you so much. I conclude my presentation here.
Thank you, Professor Siddiqui, for your wonderful talk.
Thank you so much.
Quickly, we need to pass on some queries from the participant to you.
Right.
The first query is, will it be advantageous to use MIMO antennas for low power biomedical WPT system?
Yes, definitely. MIMO antennas, because of direction of arrival and all those aspects of having, again, it's because you don't know where the power is coming from. So MIMO would be useful. This is a very wide area of wide scope of research in this area. You can literally have any, it's like old wine in new bottle. You can have any existing antenna or design new antennas to see the end is that how much power we are able to capture. So any kind of antenna, any new type of antenna will be useful just as this for a study or for investigation.
Okay. Will UWB technology be effective for energy harvesting or WPT system? UWB antenna, UWB.
Yes, but the bottleneck will be the size of the antenna. Because if you want it for a small handheld device, then UWB antenna to fit in the UWB antenna handheld device will be a problem. But UWB antenna will give you a wide range of bandwidth and frequencies to deal with. So UWB antenna covering from 900 megahertz to the whole of ISM by GSM and ISM band will be useful.
Okay. The next query is, what is the requirement of antenna parameters for WPT and RFEH application? Is the same antenna can be used for both the application?
Well, EH is energy harvesting. So energy harvesting is basically you are capturing energy from the environment. So the antenna parameter, the gain of the antenna should be very high because you don't want the efficiency of the antenna should be very high because you don't want any because in any case the amount of power is very loose. To activate for rectification circuit to activate the diodes you need a minimal amount of threshold power so that efficiency the matching load that should be critical. So likewise like antennas for horses for courses, so you can design different antennas for different applications. For again there's near field power transfer and far field power transfer, again depending on the application, depending on the gain, depending on the how much power you need, you design that antenna.
Okay. The last question from participant side is, what is the role of Q in antenna energy harvesting? Q, quality factor.
Well, quality factor again. You want the Q to be low, but then if your antenna, if you're minimizing or making the antenna smaller, and you have to, there's a certain limitation that's a Harrington-McLean limit that you reach with the Q. So you want it to be an efficient radiator, but then you have small antennas that we know that the efficiency goes down. So that's the bottleneck. So you have to
Okay.
design an antenna with a low Q, but considering the fundamental limit of that antenna.
Okay. Now with
And
this,
any more questions,
yeah.
like that can be mailed to me, and I'll be glad to respond to those questions.
Sure.
Thank you.
Right now, no more queries left in the chat box. And with this, I pay my sincere thanks to Professor Siddiqui for this wonderful talk. Now, as the time is not allowing for further discussion, because after 7 minutes we need to enter into second link, that is for validative function. With this, we conclude ourselves here as the third lecture for 5th day Indo-Canada workshop, and I request to all of you to switch to another link which we have already shared to all of you for joining validative section. Thank you once again.
Thank you so much.
Okay.
Hello, Dr. Nasimuddin. You are there?
Hello everyone. Is the slide visible to all?
Yeah, please.
Yes, yes.
Okay. Thank you. A very good evening to all for this valedictory session of this workshop. Respected Director, Professor Shivaji Bandyopadhyay, Dean Research and Consultancy, Professor M. Ali Ahmad, Institute Coordinator, SPARC, Professor Upendra Kumar, Head of the Department Electronics and Communication Engineering, Professor K.L. Vaishnav, our entire team of SPARC project, all invited distinguished speakers, as well as some reserved invited speakers to organizing team of REHS 2020, esteemed colleagues, friends, and dear participants. A good evening and good morning to one and all present over here. On the behalf of organizing committee, I welcome you all for this valedictory session conducted after successfully completion of this 1 week long virtual workshop on RF energy harvesting system REHS 2020, jointly organized by National Institute of Technology, Silchar, India, Delhi Technological University, Delhi, India, Queen's University, Canada, and hosted by Department of Electronics and Communication Engineering, National Institute of Technology, Silchar. It has been a wonderful experience of organizing this 1 week long Indo-Canada workshop, REHS 2020, in this ongoing global COVID-19 pandemic situation. Several new things have been learned during the whole period of REHS 2020, how to use the digital platform for such a huge gathering effectively. The aim of this workshop was to provide a common platform to the researchers working or wish to explore their research skills in the area of RF energy harvesting and allied domains. The workshop has addressed several fundamental concepts related to the recent development pertaining to energy harvesting systems. At the same time, it has included in-depth discussion on various design challenges that are encountered in this field and their possible solutions. The workshop has provided not only the essential knowledge, but also a platform to the participant for exchanging their ideas and information with the respective distinguished speaker. In this workshop, total 14 distinguished speakers, including 5 foreign experts, Professor Yahya Antar from Queen's University, Canada, Professor Alphonse from NTU, Singapore, Dr. Nasimuddin, scientist from A-Star, Singapore, Professor M.S. Hashmi from Nazarbayev University, Kazakhstan, Professor M. Plandokin from IKCU, Turkey, 5 Indian experts, Professor K.J. Binoy from ISC Bangalore, Professor Ashok Dey from DTU Delhi, Professor B.K. Kannodia from JNU Delhi, Professor J.Y. Siddiqui from IRP Calcutta, Professor Chinmoy Shah from IIST Trivandrum, and 4 internal experts, Professor Brinda Bhaumik, Professor T.R. Lenka, Professor Kaushik Guha, and Professor S.K. Tripathi, all belonging to NIT Silchar, have successfully delivered talks in their respective fields of expertise. Now, we would proceed for vote of thanks one by one. Honorable Director, entire team belonging to SPARC project, invited distinguished speakers, organizing team of REHS 2020, esteemed colleagues, friends, and dear participants. I, the convener of REHS 2020, deem it a great honor to propose the vote of thanks to all who have helped us in making this virtual workshop such a resounding success. As a convener of this workshop, firstly, I would like to propose my vote of thanks to Ministry of Human Resource Development, Government of India, for funding this workshop under ongoing SPARC project. In the continuation, I must now mention my heartfelt thanks to our respected director, Professor Shivaji Bandyopadhyay, for giving us an exposure to conduct this workshop. He has always been a source of motivation and encouragement as well to do something new in the department for the overall development of the institute. Next, I would like to propose hearty vote of thanks to our Dean Research and Consultancy, Professor M. Ali Ahmad, Institute Coordinator, SPARC, Professor Upendra Kumar, Chairperson of this workshop, Professor K.L. Vaishnav, for extending their support for making this workshop successful. Next, I would like to pass my warm welcome to the entire SPARC team involved, especially Professor Yahya Antar as foreign PI, Professor Alpi Frondorfer as foreign co-PI, both belonging to Queen's University, Kingston, Professor Ashok Day as Indian co-PI belonging to Delhi Technological University, Delhi. Lastly, myself, Dr. Taimur Khan as Indian PI under this SPARC project from NIT Silchar, whose collective efforts has made this workshop possible. Next, my sincere gratitude to all the distinguished invited speakers from India and abroad, especially Professor Alphonse from NTU Singapore, Dr. Nasimuddin, scientist from Institute for Infocom Research, Singapore, Professor MS Hashmi from Nazarbayev University, Kazakhstan, Professor Landokin from IKCU, Turkey, Professor KJ Binoy from ISC Bangalore, Professor Ashok Day from DTU Delhi, Professor BK Kannodia from JNU Delhi, Professor JY Siddiqui from IRP Calcutta, Professor Chinmoy Shah from IIST Trivandrum, Professor Brinda Bhaumik, Professor TR Lenka, Professor SK Tripathi, all belonging to NIT Silchar, India. Thank you all for accepting our invitation and agreed to share your knowledge with the young participant in their areas of expertise. As no program can become successful with a single person. So I extend my big thanks to the organizing committee associated with REHS 2020, especially Dr. Ujjwal Chakravarti, Dr. Gaurav Singh Baghel, Dr. Devendra Singh Gurjar, and Dr. Naresh Babu for managing their different activities associated to this digital platform on which we all are connected this evening and was remain connected for the entire duration of 5 days of this workshop. Now, in last but not least, I extend my warmest welcome to all the participants belonging to different parts of India and US, Canada, Siberia, Turkey, Singapore, and Kazakhstan who have registered for this workshop and enjoyed all the sessions and have made this workshop a grand success. Next, feedback is very much important component to judge the success for a workshop. Keeping that in mind, I, on the behalf of organizing committee, would like to hear the overall perception from the invited distinguished speakers about REHS 2020. For that, firstly, I would like to invite Professor Yahya Antar to say a few words about the overall workshop and how was his experience before behind the conduction of this workshop.
Good evening. Can you hear me?
Yeah, we can hear you.
Yeah. Well, this has been wonderful. It's a wonderful experience. First of all, I'd like to thank the director and the team at director and the staff at NIT. Taimur, you did a wonderful job in bringing everything together, starting the project in the beginning, and I appreciate the support from the Ministry, Human Resources and Development. I would thank my team and also thank my team at Queen's University and the team from University of Delhi, Dr. Ashok Day. This has been a wonderful experience for exchange of ideas, for getting people together, and I hope the registrants have harvested some information from this energy harvesting conference, got some new ideas about antennas and subject, and most importantly, taking home the connection with the networking and so on. Well, antennas are antennas, and it would not have been possible for all of us to meet without earlier development in antennas, and it's going to be a subject of interest and development in the future. When I reflect back on the workshop, I I think it was very well organized. It's first time, and I hope that we keep doing this and more of that. And I think this was a very good experience. Quite a number of participants from India, from Canada, from around the world. So I invite all of those to keep tuned, keep involved with the rest of the community. We all one community, and I again remind you of the opportunities available through collaboration, through the IEEE Antennas and Propagation Society. Finally, personally, I would like to thank all of my, colleagues in India who collaborated. Some of them contributed here to this conference, and I cherish the involvement I have with them. Thanks again, Taimur. Thanks to the NIT respected officials, and of course, this was not have been possible without the IT team there. So thank you very much, and I thank all the speakers, and I look forward to more involvement with them. And hopefully we'll have more of this. And thank you all.
Thank you, Professor. Thank you very much for your words, for the overall organization of this workshop. Now, in continuation to Professor Yahya Antar, I would prefer to call upon Indian COPI SPARC project Professor Ashok Dey to say a few words on successful completion of this workshop.
Good evening, everybody, and I am very thankful to NIT Silchar for organizing such a wonderful and successful program during this pandemic time. And my special thanks to Dr. Taimur Khan for organizing so many people and who has given us the opportunity to exchange our ideas with different experts of our very small microwave community. And I am sure that through this program, all the participants from all over the world, they have been very much benefited from the different lectures given by the different experts from all over the world. So I'm very thankful to all of you for giving me this opportunity to speak in this particular program. And again, thank you, NIT Silchar, for giving us this opportunity. Thank you.
Thank you very much, sir, for your words. Now, next, it will be a great pleasure to invite Professor Plondokan to say a few words on the successful completion of this workshop.
I'm not sure, Dr. Frandorfer. I think he has previous involvement. So
yeah.
On his behalf, as I say, on behalf of the whole team, I thank you all for this, and I will look forward to more opportunities for that, and more collaboration with the activities, and and I hope this will bring more people into the Indian community, researchers and so on board. So thank you on behalf of Dr. Frandorfer.
Thank you, sir. Thank you. Now, I would like to invite Professor Mary Plondokan for his speech on successful completion of this workshop.
First of all, thank you very much. It was a great pleasure for me to take part into such a very nice organization, and So it was actually totally very first experience about what we have just done at this stage, to have such a very nice workshop with all your very valuable colleagues. So it was a very good pleasure, a very nice pleasure for me, and I am very, very thankful for that. And I would like to also convey you all my gratitude, especially to you, Tamer Khan. It's very, very nice. And I thank all of you in deepest sense that I had such a very big opportunity to take part into such a very nice organization. And I hope it will not be the first one. I think it is very useful for all the other audiences who have followed us by the use of the YouTube channel. So I hope we will just then try to do more as a tradition. And thank you very much all the other speakers and organizing committee and all the other staff who has also just had some part of the responsibility in this very nice organization. And I am very, very thankful, and hopefully we will just then try to continue this in next times also together. And I would like to also convey my thanks to Dr. Nasruddin as well, because he has also recommended me to you for this very nice workshop. Otherwise, I could not have had the chance maybe to be with you. I'm also very thankful for that to him. And thanks a lot.
Thank you. Thank you very much. Now in that continuation, Professor Alphonse is there. Would you like to say something, sir? Professor Alphonse?
Yeah, okay.
Okay, please.
Yeah, thanks, Dr. Taimur, for organizing a 5 days a thematic workshop on RF energy harvesting. Congratulations to the entire team, which has worked very hard continuously for 5 days and before even the workshop period also, and made it a very successful event. I reached out to many participants. It's wonderful to get the more interactive kind of a questions and answers for each lecture, and then it went on very well. So whatever may be the situation, for research, there is no barrier. That's what it showed here. So the technology helped us very much, bringing everyone to a common point, exchanging their ideas and their experiences in their own field, and sharing the knowledge to all the budding researchers of this field. Okay. Hope this kind of virtual workshops would continue, and then that makes it more people no need to travel, and then it all arranged in a very short time. I think I got an invitation in just a couple of weeks back, and then it got materialized quickly. So it's nice. So once again, I congratulate to the entire team of NIT Silchar. Thank you.
Thank you. Thank you, Professor. Thank you very much. Now, in the continuation to that one, I go back to PowerPoint slide. Yeah. The participant feedback is also important. In the end of valedictory section, each registered participant has to submit online feedback. In addition to that online feedback platform, we have created a Google Meet platform for around 180 selected participants, so that they may share their observation about REHS 2020. Few participants may share quickly as per their wish. Anybody comes forward from participant side to share few words about the workshop, what they have learned, how was their experience?
I am Shambhu Kumar from MITS Gwalior, assistant professor. Thanks for giving the best opportunity for the international level FDP sir. First time attend this type of FDP sir. Thanks for all the guest faculty for giving this opportunity, Taimur sir. Okay, thanks sir. Ashok B sir, I am coming. Ashok Ji already come my college on workshop based on antenna. So second time me giving opportunity to Taimur sir. Thanks. Okay,
Thank you. Thank you very much. And anyone else from registered participants?
Yes, sir. This is Pallab Kopai from IIT Kharagpur. So it's I am a master's
Thank you very much,
student.
sir. I have such a workshop again because it was a very good workshop, sir. I want to have such a workshop again because it was very good, sir.
Thank you.
Thanks a lot, sir. Thanks for the organizing committee.
Okay. Next, please.
Hamid Ali from Shobit University, Gango. Hamid Ali, Shobit University, Gango.
Okay.
This workshop is very for me.
You are not. Please, you are not. Hamid, you are not audible to us. Close your microphone close to your mouth. You are not audible to us.
Okay, sir. Okay, sir.
Okay. Next one, please. Anyone else from participant side?
Sir, good evening. This is Dr. Suganti speaking from Christ University, Bangalore.
Okay.
I had been attending all these sessions from the first day till today. It was really very nicely arranged, wonderful session. And the resource persons who came and spoke and presented very well, very excellently it was presented, and I liked it very much. So this kind of workshop I like to happen in future also, and I would like to get collaborated with all the experts who are in the field of energy harvestment using microstrip antennas and the related. And thank you very much for having given an opportunity to be a part of this online workshop during this pandemic period. We could learn a lot. Thank you, sir. Thank you.
Okay. Thank you
Sir,
very much.
Dr. Surendra Kumar Gupta here. I wish to speak something.
Okay. Please carry on.
Myself, Dr. Surendra Kumar Gupta. That's good evening to all, and good afternoon, good morning, whatever, to the different countries. This 5-day session coverage is almost equal to 5 weeks, and I can say in my complete duration of in this field, this is such a large coverage of the topic. I think in the field of microstrip antenna, no one topic and no one field is left untouched. So it is not only this RF energy harvesting is one of the topic, but almost all the topics are covered. And I am happy here. I am, you can say, I have done PhD under Professor Kanojia, sir. So thank you very much, sir, Taimur, sir, for organizing such a wonderful workshop globally. And it's a wonderful. Thank you very much.
Thank you, Dr. Gupta. Now, I think time is not permitting to invite some more student participants because everything is having certain period of time. Now, in continuation to that one, let me go back to my slide. Okay. Now, the SPARC, the workshop REHS 2020 is jointly organized by NIT Silchar, DTU Delhi and Queen's University, Canada. On the behalf of DTU Delhi, Queen's University, Professor Ashok Day and Professor Yaya Antar has already talked, and since last 5 days I am continuously talking on the behalf of NIT Silchar, so no need to say anything more on my part. And like our another partner, Professor Frondorfer, could not join this entire week due to some other involvement on that side. For that one, like next one, in continuation to that one, I would like finally call upon to our honorable director, Professor Shivaji Bandyopadhyay, to say a few words for the participant, for the organizing committee, as well as for overall workshop. Please, sir.
Very good evening, as well as good morning to Professor Antar. I understand in the last 5 days you had a successful workshop. I was reading through the feedback given on the chat by the different participants for this workshop. And I understand that is because before organizing this program, actually since beginning, Toimuru was actually feeling sad that's in such a lockdown situation, pandemic one. How can I organize such a program? So my job was to give him the confidence from the back, and also how the thing has to be organized. And I see that there is the set of the speakers, as someone was talking, that is not only in the case of RF energy harvesting, but in case of microstrip antenna and other areas, they have been covered so well. So I do understand that is organizing such a program and coordinating all these people, because for us it is the organizing such a program for the first time, and the organizing committee starting with Toimur and the local organizing committee members at NIT Silchar, they did a wonderful job and organizing. So the set of speakers was such an excellent one that is that kept the participants glued to the YouTube and their talk. And I do believe that is the networking is already established. We would have been happy, obviously, to have all the speakers in our campus, but given the magnitude, I understand that is that the pandemic situation has helped us a lot by organizing such a program, by taking so that in terms of the IEEE APS also, that is in the region 10, I think NIT Silchar now can take the lead of organizing such sharing of programs. And when the president-elect is in our team, so obviously that is we see a bright future ahead. I do believe that is in future we'll be able to host Professor Antar and Professor Day and Professor Frondenhofer to our campus once at least before the SPARC program ends, because so that will build the cement the relationship among ourselves. And we also wish to continue with the relationship with the other speakers who were present during these 5 days of the program. So thank you once again for all of us, from all of us to all the participants, to all the speakers, to all the organizing committee members for such a program. Thank you.
Thank you, sir. Thank you very much for your
blessing
words to all of us. Now, in that continuation, I would like to call upon chairperson of this workshop as well as head of the department EC, Professor K.L. Vaishnav, to say a few words as a vote of thanks.
Very good evening, very good mornings, very good afternoon to all. Our honorable directors and other dignitaries. I'm very happy really the way Taimur has conducted, and already said that there are more than 700 participants connected really, and the support of this all the speakers really it was excellent. So at the very outset, I must thanks to really Professor E.I.M. Antar, Queen University of Canada, for wonderful support at this age really, motivating Taimur and others, we all us, for conducting collaborations, inspiring the many peoples. I must extend my thanks to LP founder, again Queen University, Canada, for a wonderful support, because this SPARC project that is for 3 years, it has been continuing, and hope so that really the wonder collaborations will bring out more collaborative projects. I must thanks to Professor Ashok De of Delhi University. The vital tool to have the project like SPARC. And Ashok De are really involved in many ways. Sir already visited the Department of Electronics many times. And we are very happy that really sir still continue and motivating, inspiring all of us. I must thanks to Muhammad Abdullah, SPARC scholar of Queen University. Really, he is giving his valuable time. Taimur, am audible, Taimur?
Yes, yeah, you are audible, sir. Carry on.
I must thanks to Professor Alfan and NIT Singapore for wonderful deliberations. I've seen his talk. It inspired the many young peoples. As we know that this RF harvesting no longer it is only antenatics. As energy harvesting studies is a big issue, and the metamaterials and other material science is coming in a bigger way to support the stories of energy. Bigger challenge come today's scenario is the stories. The many people working on the nanotechnology, material science to improve those storage capacities, and Professor Alfan has given the touch. Really, I think inspire many of the young generations. Really, they will take the more challenge, and I hope so that their futures we can have it. As we know that RF harvesting, really everybody having the mobile device, and it's an essential part as we are going to that sort that cyber systems. We have to have end user always a sensor. Energy is a big issue for all of us. I must thanks to M. Karim from NTU again Singapore, really inspiring the being giving a valuable time to inspire the audience. And then Professor Nashimuddin that Singapore already, I think sir has already visited to the EC department. He has some sort of flavor about the EC departments. Already said at the very beginning of the inauguration program, the department is evolving. We have 32 faculties. As I said, that average age is 30, and huge potential for all of us. And then already Nashimuddin sir already visited. I hope so that you will have more collaborations in bigger way for the coming futures. I must thanks to Professor M. Palakin from Turkey. Really, already he said that nice to see, and hope so that with the Turkey we will have a more bigger way collaborations. As I said that this topic is not only the antenna, it is interdisciplinary, because the moment harvesting comes, electronic circuit is coming into pictures. So we have really another big go for electronic circuit. Then we can join also to have already me and Taimu started sharing two scholar on the energy harvesting and circuit designs. Then I must thanks to really MS Hasmi from again Kazakhstan for really for wonderful collaborations and deliberations to our audience. Then our Professor Shivam K. Cole from IIT Delhi, I think Taimur has a long collaboration with the Ulster, I think IIT Delhi, and I thanks to really Professor for supporting our faculty for bigger way to do all sort of activities. Then I must thanks to Professor B.K. Kanajua from JNU Delhi. Obviously, Taimur already said that really sir is supporting us a bigger way. I hope so that we can start thinking of more bigger way. Then KJ Binoy from IC Bangalore, Professor KJ Binoy from IC Bangalore. Really, thank you, sir. Despite busy schedules, sir really given the valuable time. Then Siddiq sir, Professor Siddiq from Calcutta University, sir might have already visited to the department of. I have seen. Then he has visited twice or thrice. Maybe he has evaluated many of our PhD thesis of the PhD scholars. wonderful and thankful really support for that. Professor Chinmoy Saha, IST Singapore, that IST Trivandrum, really thank you, sir, really giving the collaborations, and really hope so that we'll look forward to the way. Then we have internal experts from Professor Binda, Professor Tia Lanka, Dr. Kyoshi Guha, and then Dr. S.K. Tripathi. Wonderful, wonderful, really support and deliberations. And finally, really, I must thanks to our NIT's authority for supporting, because many things we need to have support from our administrations. I must thanks to this entire team of Taimur. Really, they have been working not only 5 days, before 5 days also. Making arrangement is a great deals, and that's our Dr. Devando, Dr. Ujjols, Dr. Suresh Babu. Then really everybody really helps really us really to make the event really successful, and connecting more than 700 people all online base, and supporting online platforms, all those background faculty. If I miss anyone, I do not know. Maybe Gaurav is also there. So if I miss anybody, really, and all the faculty members, many of them really motivated joining the sessions to Dr. Taimurs and other experts. I hope so that in the futures we look forward to bigger collaboration with all the experts, not only Queen University and Delhi University. We expert from Kazakhstan and then Turkey and many other universities. With this, really, I thanks for concluding. I must thanks to the others that directly or indirectly whoever been involved in this workshops. I extend thanks from the Department of Electronics and Telecommunications. With this, again, thank you all. Thank you all, please. Namaste.
Thank you, Professor Vaishnav, for your talk. Now, before coming to the concluding words, I need to mention two things. That is, first one, myself and both the scholars, SPARC scholars involved in that SPARC project have prepared their presentation, their talks, but unfortunately they have not been adjusted due to limited period of time as well as time constraint, because we cannot neither prepone before 5:30 nor can beyond 10:30 in the night. Anyway, we all three will be delivering their talks on some other occasions, no problem at all. And now next thing is, we tried our level best to make this workshop a grand success. If at any moment, especially to the participants said, if we missed anything else, for that I, on the behalf of organizing committee, apologize from the core of my heart, and we will try to improve on the next forthcoming event based on the feedback which we have collected from you at the end of each lecture, and we will be collecting from you in the end of this workshop based on that overall observation of the workshop. Then with this, now I am coming to the concluding remarks. We thank you all once again for being with us in this validity session. It has been really a great experience of using digital platform in this ongoing COVID-19 pandemic situation. Now, before saying you final bye-bye, I would request to all the registered participants for submitting the overall feedback of REHS 2020 by tomorrow, like whole night or up to tomorrow 10 AM. The link will be active. That accordingly, as per your convenience, you can submit your feedback. It will be good for all of us to analyze ourselves where we were lagging. You genuinely submit your feedback based on the overall activities of this 1 week long workshop. Now with this, I conclude myself, and bye to all. Good night and good morning to all of you. Thank you very much for being with us in this evening and making this workshop a grand success. Thank you once again. Thank you.
Thanks, everybody.
Thank you.
Thank you, Dr. Tim.
Thanks a lot.
Thank you all.
Thank you.
Thank you, one and all.
Thank you, sir.
Thank you very much, sir. Good night. And good morning.
Thank you.